James Webb didn't just spot distant galaxies, it may have caught the universe lying. The numbers break exactly where our best model swears they should be unbreakable, like a marathon where 100,000 runners start at the finish line and almost none survive the course. So if we're at mile 5, surrounded by life and light, what terrifying filter is still ahead? And what does it mean about space, gravity, and whether any civilization ever makes it through? The most unsettling discoveries are never the dramatic ones. They are not the monsters lurking at the edges of our telescopes or the rogue planets drifting through empty space without a star to orbit. The genuinely terrifying discoveries are the quiet ones, the measurements that simply refuse to obey, the numbers that arrive looking ordinary and then sit on the table like a hand grenade that nobody wants to touch. When the sky becomes a laboratory, every small discrepancy carries the potential to unravel something enormous. A fraction of a percent in the wrong direction can mean the difference between a universe that makes sense and a universe that has been hiding something fundamental from us since the very beginning. For a century, cosmology felt like a discipline in permanent ascent. Better telescopes produced cleaner data. Cleaner data produced sharper predictions. Sharper predictions produced more confidence. The circle kept tightening, and with each revolution it seemed to enclose a little more truth, a little more of the final picture. Physicists and astronomers built a model of the universe that seemed to work almost everywhere they looked, from the first light after the Big Bang to the clustering of galaxies billions of years later. That model became the standard, and the standard became the scaffolding for everything else we thought we understood about existence. Then James Webb arrived. And it did not merely extend our vision into deeper time, though it did that too. It interrogated our assumptions with a precision that no previous instrument could match. It turned infrared light into a stress test, not just for the early universe, but for the model we built to describe it. And the model, in certain critical places, has begun to show its cracks. To understand why this matters, we have to think carefully about what a scientific model actually is. It is not a story in the literary sense, not a narrative shaped for emotional resonance or dramatic arc. A scientific model is a machine. You feed it inputs and it produces outputs. You feed it the relic glow of the early universe, that ancient whisper of radiation that has been traveling since the cosmos was a few 100,000 years old, and it outputs specific predictions. It tells you what the universe should look like today. It tells you how fast it should be expanding, how massive its first galaxies should have been, how quickly structure should have assembled from the primordial fog. And then you go look. And if what you see disagrees with what the machine predicted, the error is not decorative. It is diagnostic. It is the universe writing a correction in red ink across the margin of our best theory. This is the journey we are undertaking across 7 chapters. We will follow a chain of tensions that appear unrelated at first glance, a handful of unruly measurements spread across different telescopes, different methods, different corners of astrophysics. But these tensions may not be independent. They may be symptoms of a single deep misidentification, a place where we mistook a local description for a universal law, where we treated an effective approximation as a final truth. We will track that possibility from its earliest hints in Webb's first deep field images all the way to the edges of what physics currently knows how to say. The path begins where optimism feels most justified, in the swelling census of worlds that seem built for life. Every year, our instruments find more planets in the regions around their stars where liquid water could exist. Every year, the estimate of how common Earth-like conditions might be shifts upward. And every year, the silence from the rest of the cosmos becomes a little harder to explain away. That silence and that abundance are not independent puzzles. They are two faces of the same question about filters, about bottlenecks, about what fraction of beginnings actually survive to become endings. From there, the path moves outward into the deep fields, where Webb found galaxies that had no business looking the way they looked so early in cosmic history. Galaxies that appeared too massive, too bright, too organized, too ancient for a universe that had barely had time to catch its breath after the Big Bang. Each proposed explanation for what Webb saw demands a payment somewhere else in the theory, and the payments are starting to add up in ways that feel uncomfortable. Then we confront the universe's disagreement with itself about the most basic fact of modern cosmology, how fast it is expanding. 2 methods, both mature, both precise, both repeatedly tested, arrive at incompatible answers. One method reads the ancient imprint on the sky left by the infant universe. The other method climbs a ladder of distances built from nearby stars and exploding supernovae. Both are careful, both are internally consistent, and they disagree by an amount that is far too large to blame on measurement error alone, an amount that has only grown more stubborn as the tools have improved. If that expansion rate is not merely mismeasured but truly changing character over time, then the consequences are not confined to one corner of cosmology. They ripple backward and forward through cosmic history simultaneously. A vacuum energy that was supposed to be constant turns out to be drifting. A driver of acceleration that was supposed to be the simplest possible thing turns out to have dynamics. And dynamics mean hidden degrees of freedom. Hidden degrees of freedom are where the deepest physics tends to live. Beyond all of that lies the territory of fine-tuning, the unsettling observation that the numbers describing our universe seem to click into place like an improbable combination of locks. The constants of nature are not just roughly right for the existence of chemistry, stars, and stable complexity. They appear precisely right, each one sitting in a narrow window that would close if you nudged it even slightly. Whether that precision is a coincidence, a selection effect, or a clue about something deeper in the structure of reality remains one of the most debated questions in all of physics. And finally, we arrive at the strangest ledger in the whole enterprise, the thermodynamics of black holes, where information appears to live not in the volume of a region but on its surface, where gravity and spacetime may not be the fundamental ingredients of reality at all, but emergent behavior arising from something more basic, something we do not yet have a complete name for. That possibility, radical as it sounds, is not science fiction. It is the direction that several lines of serious theoretical work have been pointing for decades, and if it is right, then the cracks in our cosmology are not embarrassing footnotes. They are the first glimpse of a deeper architecture pressing through the wall. This is an exploratory journey, not a verdict but a reckoning. We will move from crowded star fields to silent equations, from brilliant infrared arcs captured in Webb's first images to austere boundary diagrams at the edge of information theory. Throughout, we will keep returning to the same question. What kind of universe produces answers that almost fit, that work beautifully in one regime and strain visibly in another, that look like a finished theory from a distance but reveal unresolved tension up close? Before we go any further, let us know in the comments where in the world you are watching from and what time it is there. This kind of conversation belongs to everyone, and it is happening all over the planet right now. Now settle in, 7 chapters, billions of years. And a reckoning with a universe that may not be the one we thought we were living in. Picture a marathon that begins at the finish line. The banner is already behind you when the gun goes off, and the clock has already been running. 100,000 runners surge forward simultaneously into what looks like a generous open course. The morning is clean, the light is good. At mile 5, the pack is so dense that the noise of footsteps and breathing creates something that feels like momentum, like safety, like evidence that the route is forgiving and the race is fair. But this particular race is designed so that almost nobody reaches the actual finish. The course does not reveal this early. It cannot because the difficulty is not front-loaded. The bottleneck does not announce itself in the first miles, where the terrain is gentle and the crowd provides a false sense of how the rest of the route will feel. The hardest sections are tucked beyond the first easy turns, in terrain that you cannot see because the runners ahead are blocking your sightline to the horizon. The hill that thins the field is not visible from mile 5. The filter is downstream, and the crowd at your current position tells you almost nothing about survival rates at mile 20. This is the emotional logic of the great filter. The filter is whatever turns a broad field of beginnings into a thin line of endings. It is a bottleneck in the trajectory of complex systems, a threshold that most trajectories hit and do not survive. The filter can be chemical, energetic, temporal, or organizational. It can be a step in the emergence of life that almost never happens, or a step in the development of civilization that almost never succeeds, or a physical constraint on survival that becomes unavoidable once a civilization reaches a certain level of capability. What makes the filter concept genuinely unsettling is not its existence in the abstract. It is the question of location. Is the filter behind us something we have already survived that explains why we seem to be alone? Or is it ahead of us, something we are approaching without any clear warning of how close it is? The two answers have entirely different emotional textures. If the filter is behind us, then our existence is the payoff of a near-miraculous sequence of improbabilities that somehow all went right, and the silence of the cosmos reflects the rarity of that sequence rather than a universal fate awaiting all civilizations. We are the lucky ones, the statistical outlier, the one runner in 100,000 who cleared the impossible obstacle that most never got past. If the filter is ahead of us, then our apparent progress means very little. We are the runner at mile 5 who feels strong because we have not yet reached the decisive stretch. The silence of the cosmos on that reading is not reassuring. It is a warning. It says that civilizations reach approximately our level of development all the time, or at least often enough, and then they stop. They hit something, and whatever they hit, they do not come back from it. Now return to the race and apply one more layer of logic. Suppose you learn that the starting field is not 10,000 runners, but 100,000. The course has just gotten 5 times as crowded at mile 5. Does that make the finish line safer for any individual runner? It does not. The the finish is defined by the bottleneck, not by the starting field. Making the starting field larger only makes the pattern more statistically significant. More runners still moving at mile 5 increases the probability that the filter is late rather than early, because early filtering would have thinned the field long before mile 5, and the crowd around you would be much smaller. A large crowd at mile 5 is not comfort. It is evidence that the decisive sorting has not yet occurred, and that means the filter is ahead. Every new planet discovered in the habitable zone of its star adds another runner to the starting field. Every improved estimate of how common Earth-like conditions are makes the field thicker and the silence of the cosmos more paradoxical. This is the emotional sting hidden inside every headline about newly discovered worlds. They should feel like good news, and in one sense they genuinely are. They mean we are not cosmically alone in the structural sense, not floating in a universe that had only one try at something like Earth, but in another sense, they intensify the question about the finish line. If starts are common and finishes are rare, then something between start and finish is consuming almost everyone, and we are somewhere in the middle of that course, 5 miles in, surrounded by the noise of what feels like company, with no direct view of what comes next. James Webb Space Telescope was not built to study the Great Filter. It was not designed as an existential instrument, and nobody at NASA or ESA framed its mission in terms of civilizational risk assessment. Webb was built to look backward through cosmic time, to capture the infrared light that has been stretched by expansion from visible wavelengths into the longer, cooler part of the spectrum that our eyes cannot detect. It was built to see through dust, to watch the first galaxies assemble from raw hydrogen and helium, to push the frontier of observation back toward the moments when the universe was still figuring out how to make stars. Its primary mandate was to refine our understanding of origins, not to threaten our confidence in progress. Yet the earliest images carried a message that nobody had quite prepared for. Not because they showed something terrifying in the conventional sense, not because some monstrous structure appeared in the darkness or some anomalous signal interrupted the photon count. They carried a message because of what they implied about the model we trusted most to explain everything. Webb's first deep field observations suggested that the universe may not behave at its most fundamental level the way our best mathematics predicted it should. And that kind of disagreement, between prediction and observation at the foundations, does not stay confined to whatever subfield first noticed it. Meanwhile, the broader enterprise of planet finding has been accelerating on a parallel track. Kepler watched for the tiny dimming of starlight as a planet crossed in front of its star, and in doing so converted exoplanets from an open question into a census. TESS widened the search to nearer, brighter stars where atmospheres could be studied with the instruments that followed. Radial velocity searches measured the subtle wobble of stars tugged by orbiting companions. Direct imaging attempted to separate the faint reflected light of planets from the glare of their host stars. Each method pushed in the same direction, transforming habitable worlds from a theoretical expectation into a documented reality across our galaxy. The numbers have become both reassuring and disturbing in equal measure. Roughly 1 in 5 sun-like stars appears to host a planet in the region where liquid water could exist on the surface, assuming appropriate atmospheric conditions. The galaxy contains hundreds of billions of stars. The implications of that arithmetic are either exhilarating or claustrophobic, depending on which end of the filter question you are currently contemplating. Exhilarating because life may be everywhere. Claustrophobic because if life is everywhere and we cannot see it, something is removing it, and that something still applies to us. The habitable zone concept has become more nuanced with each passing decade of research, and that nuance matters because it changes the census. A planet in the right orbital range still needs to retain an atmosphere, maintain a stable climate over geological timescales, avoid sterilizing radiation from an active star, and navigate the chemical prerequisites for biochemistry. Each of these requirements is a filter of its own, a narrowing of the set of worlds that make it from promising beginning to functional habitat. When astrobiology asks how common life is, it is really asking how long the filter chain is and how tight each individual bottleneck is along that chain. Even if each step seems individually plausible, a long chain of individually plausible steps can produce a vanishingly small overall probability, and that probability is what the silence of the cosmos is measuring. This documentary does not resolve the Great Filter. Nobody currently can. But it uses the filter as a frame for understanding why the cosmological anomalies we will examine are not merely academic puzzles for specialists. They are relevant to the deepest question any civilization can ask about itself, which is whether it has a future. If the universe is stranger than our best model, then our extrapolations about long-term survival are built on foundations that are less secure than we believed. And if those foundations shift, the forecasts shift with them, quietly, without alarm, in ways that may only become visible when it is too late to use the information. Cosmology's version of the crowded Mile 5 problem is structural, and it is built into the way we do science at the largest scales. We inhabit one small region of one galaxy at one particular moment in cosmic history. We build models from everything we can observe within the limits of our instruments and our horizon. We test those models against the data available to us, refine them, extend them, and eventually treat the best performing version as a description, not just of what we can see, but of the entire universe, including the parts we cannot see, including the times before we existed, and including the regions that will never be accessible to any measurement we could make. That extension from the observable to the universal is not a logical fallacy. It is a necessary move in any scientific cosmology. But it is also where unexamined assumptions accumulate, where the model's internal consistency can be mistaken for comprehensive coverage of reality. The standard cosmological model, known as lambda CDM, is our crowded Mile 5. It explains an impressive range of observations with a small and disciplined set of parameters. It gives us cold, dark matter to seed the growth of structure, providing the gravitational scaffolding around which ordinary matter condenses into galaxies. It gives us a cosmological constant, the lambda, to accelerate late-time expansion. It gives us ordinary baryonic matter, neutrinos, and radiation in their measured proportions. With these ingredients and a handful of numbers describing the initial fluctuation spectrum, it reproduces the temperature map of the cosmic microwave background, the statistical architecture of galaxy clustering, the abundance of light elements synthesized in the first minutes, and the distance redshift relationship traced by supernovae across billions of light years. The agreement across these different domains, each probed by different instruments with different systematic errors, is one of the genuine intellectual achievements of the last half-century of physics. Lambda CDM is the model we trust most when we are thinking about the universe as a whole. It is also the model that Webb was expected to confirm with sharper data at earlier cosmic times. That expectation was not naive. It was based on decades of increasingly precise measurements, all pointing in the same direction, all reinforcing the same scaffolding. Webb was supposed to be the capstone, the instrument precise enough to push the model's successful track record back to the very earliest galaxies, filling in the last remaining blanks in the story of cosmic assembly. Instead, Webb's first deep field observations introduced a different kind of story, one that will take the rest of this film to fully trace. A deep field image is not what it looks like. From the outside, it resembles a beautiful photograph of the night sky, richly populated with galaxies in different shapes and colors and orientations. But the process that produces it has almost nothing in common with ordinary photography. A deep field is a deliberate accumulation of time. The telescope stares at a single small patch of sky for hours or days, collecting photons with the patience of a geologist watching erosion. Individual exposures are stacked and co-added after careful subtraction of noise sources, cosmic rays, detector artifacts, the thermal glow of the instrument itself, the scattered light of the zodiacal dust, and the faint infrared emission of Earth's atmosphere. What emerges from that subtraction and stacking is not a snapshot of how the sky looks at one moment. It is an excavation, a dig through cosmic time, where depth corresponds to distance and distance corresponds to the past. When Webb stares into a deep field, it is seeing the universe at many different epochs simultaneously, because light from different distances has been traveling for different lengths of time. A galaxy at moderate redshift emitted its light a few billion years ago and is seen as it was then, not as it is now. A galaxy at high redshift emitted its light when the universe was only a small fraction of its current age, and appears in the image with that ancient configuration frozen in the photons that have just reached Webb's detectors after a journey measured in billions of light years. The measurement of redshift is the foundation of everything else. Redshift tells us how much the universe has expanded since the light was emitted, and from that expansion factor, combined with a cosmological model, we can calculate the distance, the look-back time, the epoch of cosmic history in which the light originated. The concept sounds mechanical, and at the level of wavelength measurement it is. But interpreting redshift as a distance requires a model of how expansion proceeded over time, which means the measurement is entangled with the theory from the very beginning. This entanglement is not a methodological flaw. It is the unavoidable structure of observational cosmology, where every observed quantity must be translated through a set of assumed physical laws to become a physical quantity. The question is always whether the assumed laws are the right ones. In Webb's first deep fields, a cluster of sources appeared that seemed wrong in a specific and systematic way. These were galaxies at very high redshifts, seen when the universe was less than 500 million years old, sometimes much less, and they carried properties that the standard model predicted should not exist yet. Their inferred stellar masses were too large, their light was too bright, their morphology suggested a degree of organized structure that takes time to develop, yet the time available had apparently been insufficient to produce it. The word impossible appeared in discussions, though careful scientists used it with qualifications attached, not impossible in the sense of violating physics. Impossible in the sense of improbable, given what the standard model predicted for the abundance and properties of structures at that epoch. The visual impact of these objects in the deep field images is genuinely strange once you know what you are looking at. They appear as tiny smudges on the infrared mosaic, almost indistinguishable by eye from the other countless galaxies in the field. Their smallness on the sky is itself a physical statement about cosmic distance, but the numbers attached to them by the pipeline that processes the photometry tell a different story. Redshift 12, redshift 15, masses comparable to galaxies that took billions of years to build, present when billions of years had not yet elapsed. Redshift 12 corresponds to a cosmic age of roughly 400 million years. Redshift 15 corresponds to something closer to 200 million years, barely more than 1% of the universe's current age of approximately 13.8 billion years. In that window, the standard model allows for the formation of the first stars and the beginning of the first primitive galaxies. What it does not comfortably allow for is the existence of massive, apparently mature galaxies with organized structure and large accumulated stellar populations. Building such a galaxy requires a sequence of steps, each with its own timescale. Gas must fall into dark matter halos. It must cool and fragment into molecular clouds. Those clouds must collapse to form stars. The first generation of stars must live and die and enrich the gas with heavy elements. Subsequent generations must form in that enriched medium. The stellar population must accumulate to the observed mass. And all of this must happen without most of the gas being expelled by the violent feedback of supernovae and radiation pressure. Tighten all of those steps into a few 100 million years, and you start running into problems with the physics of each individual step. The first reaction of any careful scientist confronted with such a result is to interrogate the measurement itself. This is not skepticism in the pejorative sense. It is the appropriate response to a claim that, if true, would force a revision of a well-tested and highly successful theory. The measurement must be checked in every dimension where it might have gone wrong before the theory is blamed. That checking process is long and unglamorous and looks from the outside like scientists refusing to accept an exciting result. In reality, it is exactly the process that makes the eventual conclusions trustworthy. An anomaly that survives scrutiny is worth more than 10 anomalies that collapse under examination. Photometric redshifts are the first place to look for errors. Most of the initial high redshift candidates in Webb's deep fields were identified through photometry rather than spectroscopy. Photometric redshift estimation works by measuring how bright a galaxy appears in several different wavelength bands and fitting those measurements to model spectra. The fitting works because galaxy spectra are not featureless. They contain abrupt changes in brightness at specific wavelengths, most notably the Lyman break, where hydrogen absorbs photons at short ultraviolet wavelengths. As a galaxy moves to higher redshift, that break shifts to longer wavelengths, eventually moving into the infrared range where Webb excels. A galaxy that appears faint or invisible in blue filters but bright in red filters is a dropout candidate, a galaxy whose Lyman break has moved past the blue filter's sensitivity range. The problem is that other physical effects can also make a galaxy faint in blue light. Dust absorbs short wavelength light efficiently and re-emits it at longer wavelengths. Old stellar populations produce less ultraviolet light than young ones. Strong emission lines can dominate a single filter's measurement and distort the apparent color. A galaxy at moderate redshift with heavy dust extinction can mimic the photometric signature of a galaxy at very high redshift with clean spectral features, because both can appear faint in blue bands and relatively bright in red bands. The degeneracy is genuine and well documented, and it is the most common explanation for high redshift candidates that later turn out to be closer imposters when spectroscopy resolves the ambiguity. Spectroscopy cuts through this ambiguity because it spreads the galaxy's light across wavelengths finely enough to identify individual spectral lines or resolved breaks rather than relying on integrated brightness in broad filters. Confirmed spectroscopic redshift requires identifying multiple features consistently, ruling out alternative line identifications that could place the galaxy at a very different distance. Spectroscopy is slower and more photon-hungry than photometry, so it cannot reach as many objects in a given observing time, but its conclusions are far more secure. As spectroscopic follow-up accumulated on Webb's most intriguing candidates, a predictable pattern emerged. Some candidates moved. A galaxy initially assigned a photometric redshift of 12 turned out, under spectroscopic examination, to be at redshift 3 or 4, much closer, much less extreme, no longer a challenge to the standard model's predictions. Some of the most dramatic headlines quietly dissolved, not with fanfare but with the gradual accumulation of spectra that placed the offending galaxies back in safer territory. This is not a failure of Webb or of the process. It is science working as intended, correcting itself through better data. But the pattern did not vanish entirely. After the spectroscopic revisions, there remained a population of galaxies that still looked problematic. Not every candidate was explained away. The statistical distribution of inferred masses and luminosities at high redshift remained elevated compared to what lambda CDM predicted, even after the most dramatic individual cases were revised. The tension shifted from this one impossible galaxy to the distribution looks strained, and that is a more serious kind of problem. A single outlier can always be absorbed as a statistical fluctuation or a measurement error. A shifted distribution that persists across multiple independent fields and multiple analysis pipelines suggests something more systematic. Gravitational lensing is another potential explanation that must be carefully evaluated. Massive structures in the foreground can bend and magnify the light from background galaxies, making distant objects appear brighter than they actually are. If a background galaxy is magnified by a factor of several, its apparent brightness implies a stellar mass several times larger than its true mass, potentially placing an ordinary galaxy into the apparently impossible range. Lensing magnification is a real effect. It happens throughout the universe, and the deep fields frequently show evidence for it in the form of stretched arcs and multiple images of the same background source. But lensing of sufficient magnitude requires specific geometric alignments of foreground mass and background galaxy, and the probability of such alignments is calculable from the statistics of foreground structures. If lensing is invoked to explain a large fraction of anomalous candidates, it requires more such alignments than the foreground mass distribution can plausibly provide. The stellar initial mass function, which describes how many stars form at each mass within a given molecular cloud, is another lever that could in principle change the interpretation of early galaxy observations. Massive stars dominate a galaxy's light output because they are enormously more luminous than their lower mass counterparts, even though they make up a small fraction of the total number of stars. If the early universe formed proportionally more massive stars than star-forming regions do today, galaxies would be brighter per unit of total stellar mass than models assuming a standard initial mass function would predict. Invoking a top-heavy initial mass function could reduce the stellar mass inferred from a galaxy's luminosity, potentially bringing an apparently massive early galaxy into alignment with model predictions. But this fix is not free. A top-heavy initial mass function also changes the rate of supernova explosions, the production rate of heavy elements, the ionizing photon budget that drove cosmic reionization, and many other observables that are independently constrained. A modification large enough to significantly ease the mass tension would likely worsen tensions elsewhere in the model's accounting. Stellar population synthesis models, the computational frameworks that translate observed spectra and photometry into physical properties like age, mass, and star formation rate, carry their own uncertainties that become more significant at high redshift. These models must account for the full complexity of stellar evolution, including poorly understood phases like the thermally pulsing asymptotic giant branch, horizontal branch morphology, and very massive star evolution, all of which can affect the integrated light of a stellar population in ways that current models handle with varying degrees of confidence. Different stellar population synthesis codes make different choices about these uncertain phases, and those choices can shift inferred stellar masses by factors that matter when comparing to model predictions. The uncertainties are larger at high redshift, where metallicities are lower and populations are younger, precisely the regime where the tension is sharpest. The picture that emerges from all of this scrutiny is not one of fraud or methodological failure. It is one of genuine uncertainty at the boundaries of what our models were designed to handle. The measurement chain from photon count to physical interpretation involves multiple steps, each with its own assumptions, and those assumptions were calibrated primarily on observations of nearby galaxies where the physics is better constrained. Extending that chain to redshifts of 10, 12, or 15 is an extrapolation, and extrapolations always amplify hidden biases. The fact that the anomalies survive careful scrutiny and revision, though at reduced significance compared to the initial reports, is what keeps the scientific community engaged. It is also what keeps the question genuinely open. What does it mean for the standard model if the tension is real? The model's predictions for the abundance of massive early galaxies come from N-body simulations that track the growth of dark matter halos from the initial fluctuation spectrum through to the present day, combined with prescriptions for how baryonic physics converts gas into stars within those halos. The prescriptions for baryonic physics are the weakest link in the chain because they involve turbulence, magnetic fields, radiation pressure, and feedback from supernovae and active galactic nuclei, all of which operate on scales far smaller than those resolved by cosmological simulations. Those prescriptions are encoded as subgrid models, parameterized recipes that capture the aggregate effect of small-scale physics without resolving it directly. Different choices of subgrid parameters can produce significantly different galaxy populations at high redshift, which means the model has more flexibility than it sometimes appears, increasing the star formation efficiency at high redshift, allowing halos to convert a larger fraction of their gas into stars on shorter timescales, can produce more massive early galaxies, but this change must be paid for. Higher efficiency means more energy released by supernovae earlier, which affects the thermal state of the surrounding intergalactic medium and the progress of cosmic reionization. It also affects the chemical enrichment history and the properties of galaxies at later times. A fix that works at redshift 12 but breaks the model's agreement with observations at redshift 3 is not a fix. It is a relocation of the problem. Reducing the strength of feedback from supernovae and active galactic nuclei is another lever. Weaker feedback allows gas to stay bound in halos more effectively, building stellar masses more quickly. But weak feedback produces galaxies that are too compact, too metal-rich, and too star-forming at late times, in conflict with the observed quiescent population of massive elliptical galaxies that stopped forming stars billions of years ago. The late-time observations that support lambda CDM were not built on naive assumptions. They were built on a feedback prescription that had been tuned to match a wide range of observational constraints. Loosening that prescription to accommodate early galaxy anomalies is not a free move. This is the deepest form of the problem. The standard model is not a simple theory with a few easily adjusted parameters. It is an interconnected system where each parameter propagates its influence through the entire history of cosmic structure formation. Adjusting one parameter to ease one tension tends to create strain somewhere else. The model's internal consistency, which is one of its genuine strengths, becomes a constraint on how much any single piece can be changed without breaking other pieces. And when the anomalies persist across multiple observational domains, the required adjustments begin to accumulate, and the model starts to feel like a collection of patches rather than a unified description. One researcher, looking at Webb's early results in this context, offered a comment that has since become something of a touchstone in popular accounts of this period. Looking at these early galaxies, they said, feels like looking at something that does not belong to our universe. The statement is not literally true in any physical sense, because the photons are real and the sky is the sky. But psychologically and scientifically, it captures something precise. It names the gap between the universe as the model describes it and the universe as the instruments are now measuring it. When an expert who has spent a career building the theoretical framework for early galaxy formation looks at new data and reaches for that language, it is worth pausing. It is the sound of a model under pressure at its strongest point. The early universe is where lambda CDM is most confident. The cosmic microwave background, the cleanest and most precise cosmological data set we possess, was produced in the early universe, and the model fits it exquisitely. The initial conditions inferred from that fit drive everything else. If the early universe is assembling structure faster than those initial conditions permit, the implications do not stay local. They propagate, they touch the timeline, they touch the expansion history. And they connect to a separate but related anomaly that has been building in precision for years, the disagreement about how fast the universe is currently expanding. That disagreement has a name, a history, and a significance that goes well beyond the measurement itself. It is called the Hubble tension, and it has become the most talked about problem in cosmology precisely because it refuses every attempt at resolution, and because its implications, if it cannot be resolved through improved measurements, are foundational. Two rulers, both carefully built, both repeatedly tested, both internally consistent, measuring the same quantity from different directions and arriving at incompatible answers. The gap between them is not an error bar problem. It is a structural mismatch that asks us to reconsider what we think we know about the bridge between early and late cosmic history. Before we follow that tension into its own chapter, take a moment to absorb what has been established so far. Webb arrived at a universe that looked too mature too early. The anomalies survived scrutiny at reduced significance. The model's flexibility, though real, is constrained by the interconnectedness of its predictions. And the question of whether the standard picture is locally successful but globally incomplete has moved from the margins of cosmological discourse to its center. The most important measurements are often the ones that look almost fine, where the disagreement is not dramatic enough to declare a revolution but persistent enough to prevent closure. That is exactly where cosmology finds itself now. Almost fine, not quite right, and getting harder to ignore. The Drake equation is one of the most famous thought experiments in science, and its fame rests partly on a paradox. It was designed to organize ignorance, to lay out the factors that determine how many communicating civilizations might exist in the galaxy, without pretending to know the values of those factors. Frank Drake wrote it on a blackboard in 1961 at a conference in Green Bank, West Virginia, and the equation has been recited in introductory astronomy courses ever since. Its terms march from the rate of star formation through planetary systems, habitable planets, life, intelligence, technology, and finally longevity, the fraction of a civilization's existence during which it might be detectable. Multiply all those terms together, and you get an estimate of how many civilizations might be out there right now. The equation's enduring value is pedagogical rather than predictive. It shows how the answer depends on a chain of probabilities that compound against each other, so that a near-zero value for any single term collapses the final product towards zero regardless of how generous the other terms are. It is a demonstration of how easily complexity can fail to produce detectable outcomes even in a universe full of suitable environments. But it is also a demonstration of how our uncertainty is structured, of which terms we know reasonably well and which terms we are essentially guessing. Star formation rates are measured. The fraction of stars with planets has been transformed from speculation to census by Kepler and TESS. The fraction of planets in the habitable zone is constrained by observation, even if the definition of habitable continues to evolve. But the terms for life originating, intelligence emerging, technology developing, and civilizations surviving are almost completely unconstrained by data. We have one example of each, and a sample size of one does not support statistical inference about the underlying probability. We can argue about what that one example implies, but the argument will always be limited by the knowledge that we might be a typical outcome, or we might be an extreme outlier, and the data cannot currently distinguish between those possibilities. This is where the great filter intersects with the Drake equation. The filter is the term or terms in the Drake equation that are nearest to zero. If the filter is behind us, it corresponds to one of the early terms, perhaps the origin of life from chemistry, or the transition from simple to complex cells, or the development of multicellularity. These are events that required very specific conditions and perhaps also extraordinary luck, and if they are genuinely rare, then life itself might be vanishingly uncommon, even in a galaxy full of habitable planets. On that reading, our existence is already the prize, and the silence of the cosmos is explained by the rarity of getting this far. If the filter is ahead of us, it corresponds to one of the later terms, perhaps the longevity of technological civilizations, or the survival of civilizations past the point where they develop weapons capable of civilizational-scale destruction, or some physical constraint that becomes unavoidable at certain technological levels. On that reading, civilizations reach our current state of development regularly enough, but almost none of them survive the next transition. The silence of the cosmos reflects not the rarity of beginnings, but the ubiquity of endings. The distinction matters enormously for how we interpret the world around us. If the filter is behind us, then finding microbial life elsewhere in the solar system would be deeply reassuring. It would confirm that the early steps are not extraordinarily rare and that our existence is not a singular miracle. If the filter is ahead of us, then finding microbial life elsewhere would be one of the most terrifying discoveries in human history, because it would mean the early steps are common, and the silence of the cosmos must be explained by something later, something that we will eventually face. The absence of extraterrestrial civilizations becomes harder to explain the more we populate the early stages of the Drake equation with plausible probabilities, and every new habitable world discovery makes the question more urgent. This is the context in which Webb's early galaxy observations carry a meaning beyond their immediate astronomical content. They are not directly about the great filter or about the search for life. But they are about the reliability of our best model of the universe, and that reliability is the foundation on which all of our other confident extrapolations rest. If the standard cosmological model is straining at its foundations, then our confidence in our understanding of physical laws and cosmic histories, and therefore our confidence in our estimates of what is possible and what is likely across the universe, is less secure than we thought. The model is not just a story about the past. It is also the framework we use to make inferences about the future, about what kinds of transitions are physical possible, and about how the universe's evolving properties create or remove opportunities for complex systems to persist. That is why a documentary about Webb's early galaxy results, the Hubble tension, and dark energy drift belongs in the same conversation as the Great Filter and the silence of the cosmos. These are not separate topics that happen to share screen time. They are connected at the level of epistemology, of how we know what we know and how confident we can be in what we think we understand. When the tools that should be converging on a single self-consistent picture of the universe instead reveal persistent internal tensions, the appropriate response is not to bracket those tensions as technical details and continue extrapolating as if everything were settled. The appropriate response is to take seriously the possibility that the model is missing something and to ask what that missing thing might be. The standard model of cosmology did not arrive fully formed from any single observation or theoretical breakthrough. It assembled over decades through the convergence of multiple independent lines of evidence, each one carrying its own systematic uncertainties, each one initially uncertain enough to permit a range of cosmological parameters, but collectively narrowing toward a single self-consistent picture. The history of that convergence is a story of instruments improving, methods maturing, and theoretical frameworks surviving increasingly stringent tests. Understanding where the model came from matters for understanding why the current tensions are significant, because they do not represent a failure of a naive or early version of the theory. They represent strains in a mature and carefully tested framework. Modern expansion of the universe was established observationally by Edwin Hubble's measurements of distances to what were then called nebulae, combining distance estimates from Cepheid variable stars with recession velocities measured from spectral redshifts. Hubble's original constant was wrong by a large factor because his distance calibration was poor by later standards, but the qualitative conclusion that the universe is expanding was correct and has been confirmed by every subsequent measurement. The history of the Hubble constant between Hubble's original estimate and the modern precision measurements is a story of systematic error hunting, of realizing that the distance ladder had rungs that were more treacherous than initially appreciated, and of building more and more redundancy into the measurement to catch biases before they could propagate. The cosmic microwave background was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who noticed an unexplained uniform signal coming from all directions in their radio telescope and eventually identified it as the relic radiation of the hot early universe that had been predicted theoretically. Subsequent experiments measured the CMB's temperature with increasing precision, culminating in the COBE satellite's discovery in the early 1990s that the background contained tiny temperature fluctuations at the level of 1 part in 100,000. Those fluctuations were the seeds of all subsequent structure, the initial conditions for everything that followed, and they became the most precise constraint on cosmological parameters available. WMAP and then Planck pushed the CMB measurement to extraordinary precision, characterizing the temperature fluctuation pattern across the entire sky with enough resolution to extract multiple acoustic peaks and measure their positions and amplitudes. The acoustic peaks carry information about the universe's composition, geometry, and expansion history in a form that is largely insensitive to the specific astrophysical modeling required by other probes. The CMB is the purest available relic of early physics, and its interpretation rests on the most fundamental physics we have: statistical mechanics, thermodynamics, and the behavior of photon-baryon plasma in an expanding spacetime. The agreement between Planck's measurements and the predictions of lambda CDM, given its best-fit parameters, is one of the most precise agreements between theory and observation in the history of science. Type Ia supernovae became the third pillar of the Standard Model when two independent teams in the late 1990s used them to measure the expansion history at intermediate redshifts and found that the universe was accelerating. This was the discovery that introduced the cosmological constant back into cosmology after decades of irrelevance, because acceleration required a source of energy that does not dilute with expansion, something whose negative pressure drives the universe to expand faster rather than slower. The cosmological constant, a term Einstein had introduced and then removed from his equations, fit the supernova data naturally, and subsequent observations using different methods confirmed the acceleration. Lambda CDM was born in its modern form from that convergence, inheriting the cosmological constant as an ingredient alongside the cold dark matter that earlier structure formation arguments had already established as necessary. The model's successes since then have been broad and impressive. The statistical properties of galaxy clustering match predictions from Lambda CDM simulations across a wide range of scales. The abundance of galaxy clusters as a function of mass and redshift tracks the growth of structure in ways that are sensitive to both dark matter and dark energy. Big Bang nucleosynthesis, the synthesis of light elements in the first minutes of the universe, agrees with observationally determined abundances in ways that constrain the baryon density independently of the CMB. Baryon acoustic oscillations in galaxy clustering provide a standard ruler that tracks cosmic distances across a range of redshifts, providing a geometric anchor for the expansion history that is independent of the supernova distance ladder. All of these successes are real. The model has earned its status as the standard. The question being pressed by current observations is not whether Lambda CDM is a good description of many aspects of the universe. It is whether Lambda CDM is a complete and correct description, or whether it is an extremely good approximation that is beginning to show its limitations at the edges of observational precision. The history of physics is full of theories that were exactly right in the regime where they were tested and had to be extended or replaced when that regime expanded. Newtonian mechanics was not wrong in the regime where it was developed. It was incomplete in the regime of very high velocities and very strong gravitational fields where special and general relativity became necessary. Classical electromagnetism was not wrong in the regime where it was applied. It was incomplete in the quantum regime where field theory became necessary. Lambda CDM may be occupying a similar position, an accurate effective description of the universe in the regimes that previous instruments could access, requiring extension in the regimes that Webb and Dacey and the next generation of surveys are now opening. The word extension sounds modest, but extensions in fundamental physics can be anything but. The extension from Newtonian to relativistic mechanics changed our understanding of space and time at the most fundamental level. The extension from classical to quantum electromagnetism changed our understanding of the nature of fields and particles. An extension of Lambda CDM that resolves the Hubble tension, the early galaxy anomalies, and the hints of evolving dark energy might require changes at a similarly foundational level. It might require revising what we think dark energy is, or what we think dark matter is, or how we think gravity behaves on cosmological scales, or how we think information is encoded in the structure of spacetime itself. That is the territory this film is mapping. Not from a position of certainty about what the right answer is, because nobody currently knows, but from a position of taking seriously the possibility that the answer, when it comes, will not be a minor calibration correction. It may be a genuine shift in how we understand the universe at its most fundamental level. And if it is, then the confidence we have been lending to our extrapolations about everything from cosmic history to civilizational futures will need to be recalibrated along with the constants. The journey ahead through this film's 7 chapters is structured to follow the chain of implications rather than the chain of discoveries, moving from observational anomaly to theoretical implication in a sequence that tightens progressively. We begin with Webb because Webb is the newest instrument pressing on the oldest questions. We move to the Hubble tension because it connects Webb's early galaxy results to a much older and more precisely characterized disagreement about the universe's basic expansion rate. From the Hubble tension, we follow the thread to dark energy, because the expansion rate and the nature of dark energy are intimately linked, and evidence that dark energy is not a simple constant is evidence that the bridge between early and late cosmic history is more complex than Lambda CDM assumes. From dark energy, we move to fine-tuning, because an evolving dark energy is a parameter that changes, and parameters that change raise questions about why they took the values they did at the times they did, and whether those values could have been different. Fine-tuning in physics always sits near the boundary between physical explanation and deeper mystery. From fine-tuning, we make the largest conceptual leap in the film, into the territory of holographic ideas and emergent spacetime. This is where the most speculative and the most mathematically sophisticated current thinking lives. It is also where the most radical potential resolution of the cosmological tensions may eventually be found. If spacetime is not fundamental, if gravity is an emergent phenomenon arising from a more basic description of information and entropy, then the problems with the standard cosmological model might reflect not a failure of one effective theory, but the beginning of a transition to a fundamentally different understanding of what space and gravity are. That transition would not be the first time in physics where a revision of fundamental ontology resolved apparently separate empirical puzzles simultaneously. The discovery that light is a wave in a field that does not require a medium resolved the contradictions of 19th century optics. The formulation of quantum mechanics resolved the inconsistencies of classical physics at the atomic scale. Each revolution looked like a series of disconnected anomalies until the right conceptual framework made them cohere. This film does not claim to have found that framework. It claims that the current set of cosmological anomalies has the character of the early stages of such a transition, where the data is ahead of the theory, where the instruments are outrunning the models, and where the shape of the problem is becoming clearer even as the solution remains distant. That is a particular kind of exciting scientific moment, uncomfortable for those who prefer settled frameworks, thrilling for those who sense that something fundamental is in motion. The goal here is to share the texture of that moment with as much honesty and precision as a documentary can manage, neither overstating the certainty of crisis nor dismissing the genuine significance of what the new instruments are finding. The marathon metaphor will return throughout. We use it not because space exploration or physics is a race in any competitive sense, but because the structure of the metaphor captures something real about the relationship between early success and later challenge. A universe full of promising beginnings is not a universe full of successful endings. The crowded mile 5 is not a guarantee that the finish line is accessible to most runners. And the fact that our instruments are good enough to see both the crowd at mile 5 and the wobble in the mile markers is the beginning of wisdom, not the end of it. It means we are in a position to ask better questions than we could before. And asking better questions, even when the answers are not yet in sight, is the most honest form of progress available. We begin now with the deep fields, with the light that has been traveling since the universe was young, and with what that light is telling us about a model we trusted. The photons have arrived, the pipelines have processed them, the anomalies have survived scrutiny, and somewhere in the gap between prediction and observation, the next chapter of cosmology is beginning to write itself. The Hubble tension is not a new problem dressed in new clothing. It has been building for years, accumulating significance the way a river accumulates volume, quietly at first, then with a weight that becomes impossible to ignore. Its roots go back to the fundamental question that Hubble himself was trying to answer when he first measured recession velocities and distances in the 1920s. How fast is the universe expanding right now, at this moment in cosmic history, as seen from our particular location within it? That question sounds simple. It has resisted a clean answer for a century. And in the modern era of precision cosmology, the attempt to answer it has produced the most consequential disagreement in contemporary astrophysics. The expansion rate today is parameterized by a single number called h0, the Hubble constant. In formal units, it is expressed in kilometers per second per megaparsec, which translates straightforwardly into plain language as the recession speed that two objects separated by a megaparsec accumulate purely from the expansion of space between them. A megaparsec is roughly 3.25 million light-years. So h0 is a statement about how quickly the universe is stretching at the current epoch, expressed per unit of separation. In an accelerating universe, this number is not the same at all times. It has a value today and different values at earlier epochs. What we call the Hubble constant is strictly speaking a snapshot of the expansion rate at the present moment, embedded in a longer history of changing rates. Two methods dominate the modern measurement of h0, and they anchor themselves in two completely different epochs of cosmic history. The first method works from the present outward, building a distance ladder from local geometric measurements through increasingly distant standard candles until it reaches the Hubble flow, the regime where recession velocities from expansion dominate over the peculiar velocities induced by local gravitational interactions. The second method works from the past forward, starting with the imprint of early universe physics on the cosmic microwave background and inferring h0 by running the standard cosmological model from those early conditions to the present day. Both methods are mature. Both have been refined over decades. Both have been checked internally for consistency, and they disagree by roughly 9%, which in the context of precision cosmology is not a rounding error. It is a chasm. Understanding why this chasm matters requires understanding the logic of each method in some depth, because the disagreement is not merely a numerical discrepancy. It is a structural conflict between two ways of knowing the same thing. If both methods were using identical assumptions and the same underlying physical framework, a 9% disagreement would mean at least one of them has a 9% systematic error that has somehow escaped detection. If both methods are free of large hidden systematics, then the framework itself, the model that is supposed to make them consistent with each other, is missing something. The local distance ladder has 3 primary rungs, each calibrated by the one below it, and each extending the reach of the measurement to greater distances. The base of the ladder is geometric, requiring no physical model of stellar interiors or nuclear burning rates or stellar evolution. It uses parallax, the apparent shift in the position of a nearby star against the background of more distant stars, as Earth moves through its annual orbit around the Sun. This shift is purely geometric. The angle of the shift and the size of Earth's orbit are sufficient to calculate the distance to the star through elementary trigonometry. The angles involved are extraordinarily small, measured in milliarcseconds, which is why the measurement required the space-based precision of ESA's Gaia satellite to achieve the sample size and accuracy needed to serve as a reliable foundation for everything above it. Gaia has measured parallaxes for more than 1 billion stars, with precision sufficient to establish a geometric foundation for galactic astronomy that was unimaginable with ground-based instruments. But precision is not the same as freedom from systematic error. Gaia's parallax measurements carry a small global offset that has been identified through internal consistency checks and comparison with independent measurements from stellar eclipsing binaries and other geometric techniques. This offset, though small, propagates upward through the ladder, because any shift in the parallax 0 point shifts the calibrated distances of everything built on top of it. The community has worked to characterize this offset and apply appropriate corrections, but residual uncertainty in its value is one of the contributions to the overall uncertainty budget of the local H0 measurement. It is a reminder that even the most geometrically transparent measurement in astronomy is not immune to subtle systematic effects. The second rung of the ladder involves Cepheid variable stars, and the Cepheid period luminosity relation is one of the most important empirical relationships in the history of observational astronomy. Cepheid stars pulsate with a period that correlates tightly with their intrinsic luminosity. A Cepheid with a pulsation period of 10 days is intrinsically more luminous than one with a period of 5 days, and the relationship between period and luminosity is steep enough to be useful as a distance indicator over enormous ranges. If you observe a Cepheid's pulsation period, you can predict its intrinsic luminosity. Comparing that intrinsic luminosity to its observed brightness gives you the distance, after correcting for the dimming caused by interstellar dust along the line of sight. The relationship was discovered by Henrietta Leavitt in the early 20th century through her patient study of Cepheids in the small Magellanic Cloud, a companion galaxy to the Milky Way. Her insight was fundamental. Since all the stars in the Magellanic Cloud are at essentially the same distance from us, differences in their apparent brightness reflect differences in their intrinsic luminosity, and the period luminosity correlation she found was therefore a relationship between intrinsic properties rather than a distance artifact. The practical implication was immediately recognized. Cepheids could serve as standard candles, objects whose intrinsic brightness is known from an observable property, allowing distances to be inferred from the comparison of intrinsic to observed brightness. The challenge in using Cepheids for the Hubble constant measurement is calibrating the 0 point of the period luminosity relation to an absolute physical distance rather than a relative scale. This is where the parallax rung of the ladder connects. By measuring parallax distances to Cepheids in the Milky Way and nearby stellar clusters, the apparent brightness of Cepheids at known distances can be used to set the absolute luminosity scale of the period luminosity relation. Once the absolute scale is set, Cepheids observed in external galaxies can provide distances to those galaxies, extending the ladder beyond the range of geometric parallax. The practical complications of Cepheid measurements are numerous and have been studied intensively. Interstellar dust absorbs and scatters starlight in a wavelength-dependent way, reddening the observed colors of stars and reducing their apparent brightness by an amount that depends on the dust column density along the line of sight. If dust extinction is not correctly characterized and subtracted, Cepheid distances are biased. The wavelength dependence of extinction means that observations at longer wavelengths are less severely affected, which is part of the reason that infrared Cepheid measurements, including those enabled by Webb's infrared detectors, are valuable for controlling this systematic. Metallicity is another complication. The period luminosity relation is not perfectly universal. Cepheids in high metallicity environments, where the stellar atmospheres are enriched in elements heavier than helium, have slightly different properties than Cepheids in low metallicity environments. If the calibrating sample and the distant Cepheid sample span different metallicity ranges, a metallicity correction must be applied, and the appropriate form of that correction is a subject of ongoing debate in the literature. Different groups apply different metallicity corrections, and those differences contribute to the spread in published H0 values from Cepheid-based methods. Crowding and blending present a third challenge. Cepheids are intrinsically bright and therefore useful at large distances, but they exist in galaxies where other stars and unresolved stellar populations also contribute light. In crowded fields, the photometry of an individual Cepheid can be contaminated by the light of unresolved neighbors, making it appear brighter than it truly is, and therefore suggesting a smaller distance than the true distance. The severity of crowding depends on the angular resolution of the instrument used to observe the Cepheid. Webb's superior angular resolution compared to previous infrared instruments has allowed it to resolve stars in nearby galaxies that were blended in older data, providing new tests of crowding corrections and their impact on Cepheid-based distances. The third rung of the local ladder uses type Ia supernovae, the thermonuclear explosions of white dwarf stars that have been pushed past a stability limit, either by accreting material from a companion star or by merging with another white dwarf. Type Ia supernovae reach luminosities billions of times greater than the Sun, bright enough to be observed across billions of light years, and they exhibit a remarkably useful empirical regularity. The peak brightness of a type Ia supernova correlates with the rate at which its light curve declines after peak. Events that decline slowly are intrinsically more luminous than events that decline quickly. Applying this width luminosity correction to observed peak brightnesses standardizes the supernovae to a common luminosity scale, allowing them to serve as standardizable candles, even though individual events are not identical. The calibration of the supernova absolute luminosity scale depends on the Cepheid distances to host galaxies. A set of galaxies in which both Cepheids and type Ia supernovae can be observed provides the connection between the Cepheid distance scale and the supernova distance scale. Once calibrated, the supernova scale reaches far enough into the Hubble flow that the recession velocities of supernova host galaxies are dominated by cosmic expansion rather than by local peculiar motions, and the ratio of recession velocity to distance gives a clean measurement of H0. This is the regime where the expansion rate can be read directly from the data, without worrying about whether a particular galaxy is falling toward a local cluster or being pushed away from a nearby void. The Cepheid supernova chain, as assembled and analyzed by the SH0E's team, consistently returns values of H0 in the neighborhood of 73 kilometers per second per megaparsec, with uncertainties that have been progressively reduced over years of work and are now small enough to make the disagreement with the early universe inference statistically unavoidable. The team has applied every reasonable correction they can identify, tested their results against multiple calibration choices, and cross-checked their Cepheid measurements with independent analyses. The result does not move. H0 stays high. The tip of the red giant branch provides an independent second rung that does not rely on Cepheids. Old red giant stars in the low-mass helium-burning phase climb a branch in the color magnitude diagram toward a maximum luminosity that is set by the physics of helium ignition in the degenerate stellar core. When enough helium has accumulated, a thermonuclear flash occurs and the star transitions to the horizontal branch, but in the color magnitude diagram, this transition appears as a sharp cutoff at the top of the red giant branch, because all stars in this mass range hit the ignition threshold at nearly the same luminosity. That cutoff is the tip of the red giant branch, and it serves as a standard candle with calibration provided by parallax distances to nearby stellar populations. TRGB measurements in the halos of nearby galaxies, where crowding is reduced compared to spiral disks, provide distances that can be compared to Cepheid distances in the same galaxies and to supernova calibrations in the same systems. The agreement between TRGB-based and Cepheid-based distance scales has been a subject of detailed investigation, with different analyses finding slightly different levels of agreement depending on calibration choices and sample selections. Some analyses using the TRGB as the calibrating rung find H0 values intermediate between the high local value and the low early universe value, suggesting either that one of the methods has a residual bias or that the true answer lies somewhere in between. Other analyses find TRGB values close to the Cepheid-based results. The spread reflects genuine methodological differences and unresolved systematic effects, not contradictions among observations. The water-maser method provides yet another geometric distance technique that avoids the entire stellar distance ladder. In a small number of galaxies, water molecules in accretion disks around supermassive black holes emit powerful maser radiation at radio wavelengths. When the geometry is favorable, the orbital motion of these masers can be measured directly through proper motion and radial velocity observations, and Kepler's laws applied to the orbiting material give the physical distance to the galaxy without any assumptions about stellar physics. This method is independent of everything above, and it returns H0 values broadly consistent with the high local measurement, adding another thread of evidence that the late-time value is genuinely different from the early-time inference. On the other side of the tension, the cosmic microwave background measurement of H0 works through a completely different chain of reasoning that begins not with nearby stars, but with the physics of the infant universe. The CMB temperature fluctuations encode a wealth of information about the universe's composition and geometry, compressed into a pattern of hot and cold spots across the sky that spans a wide range of angular scales. Extracting cosmological parameters from that pattern requires a sophisticated theoretical model of how the primordial plasma evolved, how the acoustic waves propagated and eventually froze at recombination, how the photons free-streamed from the last scattering surface to our detectors while the universe continued to expand, and how various physical effects modified the pattern along the way. The key observable that connects the CMB to H0 is the angular scale of the acoustic peaks, the characteristic angular size of the temperature fluctuations, which corresponds to the physical size of the sound horizon at recombination, projected onto the sky through the angular diameter distance to the last scattering surface. The physical size of the sound horizon is set by the speed of sound in the early plasma and the time available for sound to travel before recombination, both of which depend on the composition of the early universe. The angular diameter distance depends on the geometry of the universe and the expansion history between recombination and the present day. Fitting the observed peak positions therefore constrains a combination of early universe physics and late universe expansion history. Under the assumptions of lambda CDM, with its specific choices of dark energy as a cosmological constant and cold dark matter as the dominant matter component, Planck's precise measurement of the peak positions implies H0 in the range of 67 to 68 kilometers per second per megaparsec. This is not a direct measurement of how fast the universe is expanding today. It is an inference from the early universe, run forward through the model to produce a prediction for the current expansion rate. The inference is internally consistent within the model, meaning that the same parameter values that fit the acoustic peak positions also fit the peak heights, the polarization pattern, the lensing of the CMB by intervening structure, and many other features of the CMB data. The model is not being forced to the low H0 value by one isolated measurement. It is being driven there by the collective constraint of the entire CMB data set under the lambda CDM assumptions. Baryon acoustic oscillations in the large-scale distribution of galaxies provide a complementary early universe anchor. The same sound waves that produced the acoustic peaks in the CMB also imprinted a preferred separation scale in the distribution of galaxies, because the matter that was dragged along with the acoustic wavefront is distributed with a slight statistical preference for separations equal to the sound horizon at recombination. This preferred separation, roughly 150 megaparsecs in physical units, is the baryon acoustic oscillation feature, and it serves as a standard ruler whose known physical size can be compared to its observed angular and redshift extent to measure the angular diameter distance and Hubble parameter at the redshift of the galaxy sample. Bow measurements across a range of redshifts from various galaxy surveys generally align with the early universe anchor from Planck. When bow data are combined with Big Bang nucleosynthesis constraints on the baryon density, the inferred H0 from this combination tends to fall near the Planck value rather than the local ladder value. Big Bang nucleosynthesis is independent of the CMB, relying on the observed abundances of light elements synthesized in the first minutes and on the well-understood nuclear physics of those reactions. Its agreement with the Planck baryon density is a strong indicator that the early universe parameters are correct in that regime, which makes the tension with the local ladder more difficult to dismiss as an early universe modeling error. The statistical significance of the tension has grown steadily over time. Early comparisons of local and CMB inferred H0 values showed disagreements at the 2 to 3 sigma level, which is noticeable but not compelling by the standards of particle physics or precision cosmology. As both methods improved, the tension grew rather than shrank. Current comparisons place the disagreement at 5 sigma or above, depending on which data sets and analysis methods are used. 5 sigma is the threshold that particle physics uses to claim discovery, and in the cosmological context, it means that the probability of the disagreement arising from random measurement error, assuming the model is correct, is less than 1 in a million. The tension is not a fluctuation. It is a systematic conflict. The astrophysical and theoretical community has proposed many potential resolutions, and evaluating them requires following the logic of each proposed fix through the entire web of constraints that the standard model must satisfy simultaneously. A resolution that eases the Hubble tension while worsening another well-established agreement is not a solution. It is a problem relocation. The requirement that a viable resolution must improve the overall fit to all available data simultaneously is what makes the tension so resistant to solution. Early dark energy is the most extensively studied class of resolution on the early universe side. The basic idea is to add a new energy component that was significant in the universe before recombination, contributing enough energy density to speed up the early expansion slightly relative to what lambda CDM predicts. Faster early expansion leaves sound waves less time to travel, reducing the physical size of the sound horizon. A smaller sound horizon means that the same observed angular peak positions in the CMB are consistent with a larger H0, because the ruler is shorter and must be placed at a proportionally closer effective distance to subtend the same angle. The appeal of this idea is that it modifies only the early universe expansion without directly changing the late universe behavior, which is where the local measurements are made. But the implementation requires specifying what the early dark energy actually is, what drives it, why it appeared before recombination and then faded afterward, and how its dynamics are parameterized. Various forms have been proposed, including scalar fields rolling in specific potentials and modifications to the equation of state during the early radiation-dominated era. Each specific implementation makes detailed predictions about the shape of the CMB power spectrum, the growth of perturbations, and the bow feature that differ subtly from lambda CDM and can be tested against data. Current results on early dark energy models are mixed in a way that is scientifically informative. Some parameterizations of early dark energy do improve the fit to the CMB while allowing higher H0 values. But they tend to increase the predicted amplitude of matter fluctuations, characterized by a parameter called S8, which measures the combination of the matter density and the clustering amplitude. The S8 value predicted by early dark energy models can conflict with weak gravitational lensing surveys and galaxy cluster counts at late times, which prefer lower clustering amplitudes than lambda CDM already predicts. So early dark energy may ease the Hubble tension while worsening what is sometimes called the S8 tension, trading one problem for another. Whether this trade is acceptable depends on the relative statistical significance of the two tensions and on whether the S8 tension itself reflects missing physics or observational systematics. Extra-relativistic species in the early universe represent another approach to reducing the sound horizon. Additional light particles, beyond the 3 standard model neutrinos, would contribute to the radiation energy density in the early universe. Higher radiation density means faster early expansion, reduced sound horizon, and potentially higher inferred H0 from CMB fits. The parameter used to characterize extra-relativistic species is NEF, the effective number of relativistic degrees of freedom. The standard model predicts NEF of approximately 344 after accounting for the slight heating of neutrinos relative to photons during electron-positron annihilation. Deviations from this value would signal new physics. The CMB is sensitive to NEF because extra radiation energy density changes both the early expansion rate and the detailed damping of small-scale CMB fluctuations, the smoothing of temperature variations at small angular scales by the diffusion of photons through the plasma during recombination. Planck measurements constrain NEF to be consistent with the standard value within errors that are not yet tight enough to rule out small deviations, but tight enough to limit how much extra radiation can be added without breaking the fit to the damping tail. The room for extra NEF is constrained enough that it cannot alone resolve the full Hubble tension without other modifications. Big Bang nucleosynthesis also constrains extra-relativistic species because they affect the expansion rate during the era when helium and deuterium were being synthesized, altering the predicted abundances of those elements. The deuterium abundance measured in pristine low metallicity gas clouds is particularly sensitive to the conditions during nucleosynthesis and provides a constraint on the baryon density and the expansion rate in the first few minutes that is largely independent of the CMB. These constraints are consistent with the standard NEF value, and limit the room for extra species, so this resolution is also hemmed in on multiple sides. Modified gravity theories attempt to change the relationship between the distribution of matter and the expansion of the universe in a way that could shift the inferred h0 without directly changing either the early or the local measurement. If gravity on cosmological scales behaves differently from general relativity, the mapping between density fluctuations and expansion history changes, potentially allowing a higher h0 to be consistent with both the CMB pattern and the bow distances. But modified gravity theories must pass tests on all scales, from laboratory measurements of the inverse square law to solar system orbital dynamics to the large-scale growth of structure. The parameter space of modified gravity is constrained by these tests from multiple directions, and theories that modify gravity enough to affect cosmological expansion significantly tend to introduce effects on smaller scales that can conflict with local measurements. Late-time modifications to the expansion history, through evolving dark energy or modifications to the equation of state at low redshifts, can in principle change the distance-redshift relation in a way that bridges the local and early measurements. If dark energy was more repulsive in the recent past than a cosmological constant implies, the universe could have expanded faster recently, moving the local calibrators to distances that correspond to a higher effective h0 when matched to their observed recession velocities. Late-time modifications must be consistent with the shape of the supernova Hubble diagram, which traces the distance-redshift relation across a range of redshifts and is sensitive to changes in the expansion rate. They must also be consistent with bow distances at multiple redshifts, which constrain the geometry independently. Threading both constraints simultaneously while significantly shifting h0 is geometrically difficult. The remaining possibility that the local measurement is biased requires a systematic error that is both large and coordinated across multiple independent methods. The SH0Es team has used Cepheids, TRGB has been used by other groups, water masers have provided geometric distances, gravitational wave standard sirens have provided independent distance measurements. The fact that multiple independent methods cluster near the high value makes a single astrophysical systematic explanation increasingly implausible. A bias would need to affect all of these methods in the same direction without leaving detectable residuals in the internal consistency checks that each method applies. Webb's contribution to this argument is most direct in its Cepheid observations. Webb has observed Cepheids in supernova host galaxies with a resolution and sensitivity that allows tests of crowding corrections that were not possible with Hubble Space Telescope infrared data. If crowding in Hubble-era images was causing Cepheid brightnesses to be overestimated, Webb should see lower fluxes for the same stars when the blended neighbors are resolved. Early Webb Cepheid results have been published and analyzed, and the conclusion from those analyses is that Hubble-era crowding corrections were reasonable, and that the high h0 value from Cepheids survives the Webb-era scrutiny. The crowding explanation for the Hubble tension does not appear to account for a significant fraction of the discrepancy, and the latter's high h0 result remains. This is the claustrophobia that the Hubble tension generates. Every escape route closes as the data improve. Every proposed systematic shrinks under scrutiny. Every theoretical fix either requires new and untested physics or creates a new tension to replace the old one. The disagreement is not growing noisier with more data. It is growing quieter and sharper, the two values becoming better defined while the gap between them refuses to narrow. That behavior is not the behavior of a measurement problem. It is the behavior of a model problem. What would it mean to take seriously the possibility that lambda CDM is the source of the discrepancy? It would mean accepting that the bridge the model builds between the early universe and the present day has a flaw. Some piece of physics is being applied incorrectly, some component is being omitted, some assumption embedded in the framework is wrong in a way that shifts one inferential chain relative to the other without triggering alarms in either chain's internal consistency checks. Finding that wrong assumption requires being willing to interrogate things that have seemed secure for decades, including the nature of dark energy, the behavior of dark matter, the history of expansion across cosmic time, and the relationship between the initial conditions set by the CMB and the final state measured by local surveys. This is why the Hubble tension and the early galaxy anomalies belong in the same conversation. They are both pressing on the foundations of the standard model from different directions. The early galaxies press from the past, suggesting that structure formation happened too quickly in the early universe. The Hubble tension presses from the present, suggesting that the universe is currently expanding too fast relative to what the early conditions predicted. If both anomalies are real and both reflect the same underlying model deficiency, then the model is straining not at its edges but at its center, and strains at the center propagate everywhere. The next thread to pull on is the nature of dark energy itself. Lambda is a constant, but the data may be saying otherwise. The most direct way to test whether dark energy is truly constant is to measure the distance redshift relation with sufficient precision across a wide enough range of redshifts that any evolution in the dark energy density would leave a detectable imprint on the geometry. That is precisely what the dark energy spectroscopic instrument was designed to do, and its early results have added another layer of complexity to a picture that was already under pressure. The Dark Energy Spectroscopic Instrument occupies the focal plane of the Mayall 4-meter telescope at Kitt Peak National Observatory in the Arizona desert. It is not a telescope in the conventional sense, not a single mirror focusing light onto a camera. It is more accurately described as a machine for mass-producing precise distances, a systematic engine designed to overcome the fundamental limitation of cosmological observation, which is that interesting physical signatures are statistically weak and require enormous sample sizes to detect above noise. The bow feature in galaxy clustering is a prime example. It is a gentle excess in the two-point correlation function of galaxy positions at a specific separation scale, too subtle to see in any small survey, but clean and reliable when averaged over volumes containing millions of galaxies. DAISY achieves its sample sizes through an engineering achievement that is remarkable for its combination of precision and scale. The focal plane of the Mayall telescope has been equipped with 5,000 robotically positioned optical fibers, each one capable of being directed at a specific target on the sky through a small actuator that moves the fiber tip to the required position within seconds. Each fiber feeds starlight or galaxy light into a spectrograph that records the spectrum simultaneously with all the other fibers in operation. A single telescope pointing can therefore measure spectra for up to 5,000 galaxies, quasars, or stars at once, turning what would otherwise be a painfully slow accumulation of individual measurements into an industrial-scale survey. The targets are selected from photometric surveys that have already cataloged galaxies and quasars across the sky without spectra. DAISY then goes back to those positions and measures spectra, providing the precise redshifts needed to place each galaxy in three-dimensional space, rather than projected on the two-dimensional sky. The resulting three-dimensional map grows with each night of observation, filling in the cosmic web with measured galaxy positions in a volume that spans billions of light years and multiple epochs of cosmic history. DAISY divides its targets into several classes, each occupying a different redshift range and probing a different era of cosmic history. Bright galaxies at low redshifts form the foundation of the nearby universe sample. Luminous red galaxies, massive and bright enough to be seen at moderate distances, probe intermediate redshifts. Emission line galaxies, with strong spectral lines from ionized gas that make their redshifts easy to measure, push into higher redshift territory. Quasars, the actively accreting supermassive black holes that outshine entire galaxies at their peak, extend the survey into the distant past, where individual galaxies would be too faint for efficient spectroscopy. Each tracer population comes with its own selection function and systematic uncertainties that must be carefully characterized and corrected in the analysis. The first data release from DAISY, representing the first year of observations, included tens of millions of galaxy and quasar spectra, covering a substantial fraction of the sky and a wide range of redshifts. The primary cosmological analysis focused on measuring bow at multiple redshift bins, comparing the observed scale of the baryon acoustic feature in each bin to the predicted scale under different cosmological models. The results confirmed the detection of bow across multiple tracers and multiple redshifts, providing a set of geometric distance measurements that together trace the expansion history over billions of years of cosmic time. The cosmological implications of these measurements became the focus of intense attention when DAISY combined its bow results with complementary data from supernova surveys and the cosmic microwave background. The combination of these probes constrains the dark energy equation of state, the relationship between dark energy pressure and dark energy density that determines how dark energy behaves as the universe expands. If that relationship is the simple one implied by a cosmological constant, with pressure exactly equal to negative energy density and an equation of state parameter W equal to -1, then the combination of probes should be consistent with that value. If dark energy is something more dynamical, the equation of state may differ from -1 or vary with redshift. Dacey's combined results showed a preference for dark energy behavior that departs from a pure cosmological constant. The preference is not overwhelming by the standards that would justify a discovery claim, but it is statistically significant enough to prevent dismissal as noise, and it has persisted across different choices of complementary data sets and different analysis methods. The direction of the preference is particularly interesting. The results are consistent with dark energy that was stronger in the past and is weakening in the present, or equivalently, dark energy that is becoming less repulsive over time. This is the opposite of what phantom dark energy would imply, and it is the kind of behavior that rolling scalar field models of dark energy, often called quintessence, can naturally produce. The parameterization most commonly used to describe potentially evolving dark energy expresses the equation of state as a function of the scale factor, the quantity that tracks how much the universe has expanded since the Big Bang. The simplest such parameterization uses two numbers, the current value of the equation of state and its rate of change. In the lambda CDM model, both numbers take specific values. The current equation of state is exactly -1, and the rate of change is exactly 0. Dacey's results suggest that the current value may be somewhat higher than -1, meaning less repulsive than a cosmological constant, and that the rate of change may be negative, meaning the equation of state is moving away from -1 toward less negative values as time passes. Combined, these two tendencies paint a picture of dark energy that was more lambda-like in the past and is gradually changing character. The interpretation of this result requires careful consideration of what other data sets are brought into the combination and how they constrain each other. Type Ia supernovae provide the most direct measurement of the distance redshift relation at intermediate redshifts, and their data directly constrain the shape of the dark energy equation of state. Different compilations of supernova data, reflecting different photometric calibration choices and systematic correction methods, give somewhat different constraints on dark energy evolution. When Dacey's bow measurements are combined with different supernova data sets, the preference for evolving dark energy strengthens in some combinations and weakens in others, which tells scientists that the result is sensitive to the treatment of supernova systematics and that pinning down those systematics is critical for reaching a definitive conclusion. The CMB provides a third anchor because it constrains the properties of the early universe that determine the sound horizon size. Since bow measurements use the sound horizon as a ruler, the size of that ruler feeds into all distance inferences. If the CMB constraint on the sound horizon is fixed, then Dacey's measured bow angles directly translate into distances at each redshift, and those distances constrain the expansion history. If dark energy evolves, the distances at different redshifts will trace a curved path in the distance redshift plane rather than the specific curve predicted by a cosmological constant, and that curvature encodes the evolution of the equation of state. The statistical significance of Dacey's preference for evolving dark energy is approximately 2 to 3 sigma in the most favorable combinations of data sets. This means the probability of seeing a deviation of this size or larger by random chance, if the true cosmology is lambda CDM, is roughly 1% or a few percent, depending on the specific analysis. This is not large enough to claim a discovery, but it is large enough to take seriously, particularly because it appears consistently across different redshift bins and different tracer populations in the Dacey data. A fluctuation would not typically persist coherently across the full redshift range probed by the survey. The theoretical implications of genuine dark energy evolution are substantial and ripple through cosmology in multiple directions. A cosmological constant is consistent with the idea that the vacuum of spacetime has a fixed energy density, a property of empty space itself, rather than of any dynamical field. This interpretation connects to fundamental quantum field theory, though in a deeply problematic way that we will discuss in the chapter on fine-tuning. If the cosmological constant is the correct description of dark energy, it is a fixed number built into the laws of physics, and asking why it has the value it has is a question about initial conditions or fundamental constants, rather than a question about dynamics. If dark energy is instead a dynamical field, it has degrees of freedom that evolve in time. It has an equation of motion that describes how it responds to its own energy density and to the expansion of the universe. Its current value is not a fixed constant, but a snapshot of a slowly evolving configuration. That configuration might have been different in the past and will be different in the future. The universe's expansion history is then not a path through a static background energy, but an interplay between expansion and a field whose properties change as it rolls through its potential landscape. This change of perspective has immediate consequences for the Hubble tension. If dark energy is dynamical, the expansion history at all epochs is potentially different from what lambda CDM predicts, and the mapping between the early universe parameters and the present-day expansion rate is sensitive to the form of the dark energy evolution. A dark energy field that was slightly stronger in the past than a cosmological constant implies could have accelerated the universe more vigorously during the intermediate epoch between the CMB and today, potentially shifting the relationship between the early universe sound horizon and the current expansion rate in a way that eases the Hubble tension without requiring a modification to the early universe physics. The problem is that this only works if the dark energy evolution is precisely tuned to ease the tension without conflicting with the supernova Hubble diagram, the bow distances, or the detailed CMB parameter fits. Dark energy evolution that helps in one regime tends to hurt in another, because the expansion history is constrained across all the redshift ranges where bow and supernovae are observed, not just at the specific epoch where the Hubble tension lives. The flexibility that evolving dark energy provides is real, but limited by the mesh of overlapping constraints. The growth of cosmic structure adds another layer of constraint. When dark energy is stronger, expansion is faster, and faster expansion suppresses the growth of density fluctuations because it prevents matter from clustering as efficiently. The amplitude of the matter power spectrum, the statistical measure of how clumped matter is on different scales, is sensitive to the balance between gravitational clustering and the diluting effect of expansion. If dark energy was stronger in the past than a cosmological constant predicts, the growth of structure would have been suppressed more aggressively during that era, and the matter distribution today should reflect that suppression. Weak gravitational lensing surveys, which measure the subtle distortion of galaxy shapes by the gravitational influence of large-scale structure along the line of sight, are sensitive to the amplitude of matter fluctuations. These surveys have found clustering amplitudes that are somewhat lower than what lambda CDM predicts, a discrepancy sometimes expressed through the S8 tension mentioned earlier in the context of early dark energy models. If evolving dark energy naturally predicts lower clustering amplitudes, it might ease both the Hubble tension and the S8 tension simultaneously, potentially explaining two apparently separate anomalies with one modification. But this possibility must be evaluated carefully because the S8 tension, like the Hubble tension, has both potential observational and theoretical explanations. On the observational side, weak lensing measurements require precise characterization of intrinsic galaxy alignments, photometric redshift errors, and the nonlinear regime of structure formation, where simple perturbation theory breaks down and simulations must be used. On the theoretical side, massive neutrinos suppress the growth of small-scale structure and reduce the predicted clustering amplitude, and the exact neutrino mass sum is not yet precisely determined from particle physics experiments alone. There is enough flexibility in both the observational systematics and the theoretical modeling that the S8 tension could be explained within lambda CDM without invoking dark energy evolution. The situation is therefore one of multiple overlapping hints pointing in a consistent direction, but none of them individually compelling enough to force a revision of the model. The early galaxy anomalies suggest the early universe is building structure faster than predicted. The Hubble tension suggests the present-day expansion rate is higher than the early universe implies. The Dacey results suggest dark energy may be evolving rather than constant. The S8 tension suggests structure growth may be suppressed relative to predictions. If all four of these anomalies reflect the same underlying physics, there may be a single modification to the standard model that addresses all of them simultaneously. That would be a compelling case for new physics. If they reflect independent observational systematics or statistical fluctuations, the model may survive intact after careful cleaning. The community is currently in the phase of sharpening the question rather than answering it. Each new observation provides information that can either strengthen or weaken the case for new physics, and each new theoretical proposal provides a framework that makes the case either more or less coherent. Dacey's second-year results will provide substantially more data and tighter constraints. Webb will continue to push the early galaxy measurements toward firmer statistical footing through spectroscopic confirmation and improved photometric calibration. New supernova surveys will provide refined distance measurements with better control of systematic errors. The Euclid satellite from the European Space Agency will provide an independent weak lensing and galaxy clustering survey that will either confirm or challenge the patterns emerging from current data. This is the moment before clarification, when the outlines of something potentially important are becoming visible, but the full picture has not yet resolved. It is an uncomfortable place to occupy scientifically, because the stakes of the question are high and the answers are not yet secure. But it is also, paradoxically, the most honest place in science, where the work is hardest and the knowledge is most provisional. Provisional does not mean worthless. It means subject to revision, and revision is how science earns its authority over time. The implications for the great filter question remain indirect but genuine. If dark energy is evolving, and the universe's expansion history is more complex than the simplest model assumes, then the future of cosmic structure is less certain than our current forecasts suggest. The ultimate fate of the universe depends on what dark energy does over the next many billions of years, and if it is changing now, it may change further in ways we cannot currently predict. A universe that accelerates indefinitely toward cold isolation is qualitatively different from a universe where the acceleration eventually ceases or reverses. The habitability of the far future depends on which of those possibilities is realized, and that depends on what dark energy actually is. More immediately, the possibility that our best model is incomplete in the way these anomalies suggest raises questions about what else we may have gotten wrong in our understanding of long-term physical conditions. The constants of nature, the fine structure constant, the gravitational constant, the masses of elementary particles, have all been assumed stable across cosmic time. If dark energy can evolve, other apparently fixed properties of spacetime might also evolve, and evolutionary changes to the fundamental constants would have consequences for chemistry, nuclear physics, and stellar evolution that could fundamentally alter the conditions available for complex systems. This thought is not alarmist speculation. It is a logical extension of the recognition that our assumed framework may be an approximation. If one piece of the assumed landscape is dynamical rather than fixed, the question of what else might be dynamical becomes scientifically legitimate. Searching for variation in fundamental constants over cosmic time is already an active field of inquiry, using quasar spectra and other probes to look for shifts in atomic transition frequencies that would signal changing physics. Current results are consistent with stable constants within measurement uncertainties, but the search continues, and the motivation for it grows stronger as other indications of a more dynamical universe accumulate. The chapter on dark energy does not end with a conclusion about whether the cosmological constant is truly constant. The data are not yet definitive. What it ends with is a recognition that the question is now being asked with instruments powerful enough to distinguish the answer, and that the current hints, though not yet conclusive, are pointing consistently toward a universe that is more dynamical, more complex, and less fully captured by the simplest possible model than the last 20 years of precision cosmology had suggested. The standard is under pressure from three directions at once: early structure formation, the expansion rate calibration, and the character of late-time acceleration. The pressure is not overwhelming any single constraint, but it is testing the structural integrity of the whole framework simultaneously. That kind of testing, across multiple domains at once, is when fundamental physics tends to change. Not when a single dramatic observation breaks a single rule, but when a coherent pattern of smaller tensions accumulates across enough independent measurements that the simplest explanation shifts from observational error to theoretical incompleteness. We may be in the early stages of that shift. The pattern is not yet definitive, but it is no longer easy to ignore. Return now to the fine-tuning problem, which sits at a different level of the scientific hierarchy from the empirical tensions we have been discussing. The Hubble tension and the dark energy anomalies are questions about whether our measurements of specific quantities match our model's predictions of those quantities. Fine-tuning is a question about why the quantities have the values they do at all, why the universe is configured in a way that permits the existence of anything interesting rather than an undifferentiated soup of radiation, or a collection of black holes, or a completely empty and structureless void. The numbers that define our physical reality are not derived from any deeper theory that we currently possess. The mass of the electron, the strength of the electromagnetic force, the ratio of the electromagnetic to gravitational interaction strength, the mass differences between the up and down quarks, the strength of the cosmological constant, and dozens of other parameters appear in our physical theories as inputs that must be taken from experiment rather than derived from principle. They are what they are, and the theories that use them are tested by comparing their predictions to observations, not by explaining where the numbers came from. What is striking about these numbers is not merely that they exist, but that they appear to have been selected from a much larger possible space in a way that permits the universe to contain structure, chemistry, and life. Change any of them by more than a small fraction, and the consequences are typically catastrophic for complexity. Increase the strong nuclear force by a few percent, and diprotons become stable, burning all the hydrogen in the universe to helium in the first seconds after the Big Bang, leaving no fuel for long-lived stars. Decrease it by a similar amount, and nuclei with more than one proton become unbound, leaving only hydrogen and no chemistry beyond the simplest atom. Change the mass difference between the up and down quarks and the stability of the neutron changes, altering whether atoms heavier than hydrogen can form at all. The fine structure constant, which governs the strength of electromagnetic interactions, enters everywhere in atomic physics and chemistry. Its current value, approximately 137, is what allows atoms to have the quantum mechanical structure they do, with electrons in stable orbitals at separations that permit chemistry. If it were significantly larger, atoms would be smaller and more tightly bound, chemistry would be qualitatively different, and complex organic molecules of the kind that biology uses might not be possible. If it were significantly smaller, atoms would be loosely bound, and the electromagnetic force would be too weak to hold molecules together effectively. The cosmological constant itself presents the most extreme version of this problem. The observed value of the cosmological constant, the energy density of the vacuum that drives cosmic acceleration, is approximately 10 to the power of -123 in natural units, where quantum field theory sets the scale. This is not a small number in absolute terms. It is an extraordinarily small number in relative terms, because naive calculations in quantum field theory suggest that the vacuum energy should receive contributions from quantum fluctuations of all the fields it contains, and those contributions would naturally sum to a value that is 120 orders of magnitude larger than what is observed. The discrepancy between the naively expected and actually observed vacuum energy is the largest quantitative discrepancy between theoretical expectation and observation in the history of physics. It is not a fine-tuning problem in the sense of a small adjustment. It is a fine-tuning problem that requires cancellation between different contributions to the vacuum energy at the level of 120 decimal places, with no known mechanism to enforce that cancellation. This is the cosmological constant problem, and it sits at the intersection of quantum field theory and general relativity in a way that neither theory alone can resolve. Quantum field theory predicts that the vacuum is not empty, but filled with fluctuating fields that contribute to its energy density. General relativity requires that all forms of energy, including vacuum energy, gravitate and therefore affect the expansion of the universe. The combination of these two requirements produces a prediction for cosmic acceleration that is wildly wrong. The vacuum either has far less energy than quantum field theory suggests, which would require a cancellation mechanism that does not exist in the current framework, or the cosmological constant is supplemented by other contributions that nearly but not perfectly cancel the quantum fluctuation energy, leaving only the tiny residual that drives the observed acceleration. The anthropic reasoning that is sometimes invoked to address fine-tuning problems begins from a different starting point. Rather than asking why the constants have the values they do, it asks what values are consistent with the existence of observers capable of asking the question. If the universe has a very large number of regions with different values of the fundamental constants, perhaps produced by an inflationary mechanism that creates many causally disconnected domains with different low-energy physics, then the question of why our region has the constants it does become similar to the question of why we live on a planet with a breathable atmosphere. The answer is that we could not live anywhere else, not because other places are impossible, but because they are incompatible with our existence. The anthropic argument for the cosmological constant makes a specific prediction. If the cosmological constant were much larger than observed, it would have caused the universe to accelerate so quickly that no structures could form at all, and there would be no galaxies, stars, planets, or observers. If it were negative and large, the universe would have recollapsed before structures could form. The range of values compatible with observers is narrow, and within that range, most values are close to the observed one by a logarithmic measure. So the observation that we see a small cosmological constant may not require a physical explanation beyond the selection effect of our existence. This argument is genuinely difficult to evaluate because it requires accepting a multiverse of some kind, a collection of causally disconnected regions with different physical parameters, and that multiverse is not directly accessible to observation. The question of whether the multiverse is a scientific hypothesis or a philosophical framework depends on whether the underlying physical mechanism that generates it, most commonly inflationary cosmology, makes testable predictions that can distinguish it from alternatives. Inflationary cosmology, does make testable predictions about the statistics of the CMB fluctuations and the spectrum of primordial gravitational waves, and those predictions are being tested with current and future experiments. But the specific multiverse prediction about the distribution of constants is not directly testable with foreseeable instruments. The fine-tuning problem connects to the cosmic filter in a way that is both obvious and subtle. The obvious connection is that the existence of life at all requires the fine-tuning to have been right, so in that sense every observer has already survived the fine-tuning filter by definition. The subtle connection is that the fine-tuning of each constant represents a threshold, a value that divides the space of possible physics into regions where complexity is possible and regions where it is not. If the constants were slightly different, the filter would have been absolute, eliminating all complex structures from the universe before any biology could begin. The fact that we are here means the filter at the level of fundamental constants was not absolute for us, but it says nothing about the filters that come later, after the stage of chemistry and biology and civilization. What the fine-tuning does suggest is that the universe appears structured in a way that makes complexity possible, not guaranteed but possible, in specific configurations. The number of those configurations relative to the total space of possible configurations is what gives fine-tuning its troubling character. If the space of possible constant values is truly large, and the region compatible with observers is truly narrow, then our existence requires either an explanation through selection, effects in a large ensemble, or an explanation through some unknown physical principle that fixes the constants to the values that permit observers. Neither explanation is currently available in a satisfying form. Both are active areas of theoretical investigation. For the great filter question, the fine-tuning consideration adds a layer that operates at a more fundamental level than the astrophysical or biological filters we discussed earlier. Even if life is common given the constants of our universe, those constants themselves represent a filter at the level of universes. Most conceivable universes, if such things exist in any meaningful sense, are not configured to permit life. Ours is, and that makes our existence contingent on a selection that happened at the deepest possible level of physical reality. But having survived that deepest filter does not protect against the filters that operate within our universe on timescales accessible to civilizations. The cosmic filter and the civilization filter are at different levels of the hierarchy, and surviving the first does not preclude the second. The journey through fine-tuning leaves us at a particular kind of precipice. We have established that the constants of our universe appear calibrated for complexity in a way that seems improbable from a purely random starting point, and that no current physical theory explains why they take the values they do rather than the values that would produce a sterile or structureless cosmos. We have established that the standard cosmological model is showing strain at multiple points simultaneously, and that the strain is not obviously attributable to measurement error alone. Now we need to ask what lies beneath. If the model is incomplete, what might the deeper description look like? And if spacetime itself is not the fundamental fabric of reality, what is? This is where the conversation shifts register. The empirical anomalies we have been discussing are motivations for theoretical work, not conclusions about it. The theoretical ideas we are about to explore are not established physics. They are serious proposals from serious physicists, grounded in mathematical consistency and motivated by multiple lines of reasoning, but not yet confirmed by decisive experimental tests. The distinction matters because this film is committed to honesty about what is known and what is speculated, and at the frontier of theoretical physics, the two categories exist in close and sometimes uncomfortable proximity. The starting point is black holes, because black holes are where the deepest problems in theoretical physics concentrate themselves most visibly. They are not just extreme environments for matter and radiation. They are places where general relativity and quantum mechanics are both required simultaneously, and where the predictions of each theory conflict with those of the other in ways that cannot be resolved by slight adjustments to either. Black holes are the laboratory where the limits of our fundamental theories are most starkly exposed, and the puzzles they generate have driven some of the most productive theoretical work in physics over the last 50 years. The first puzzle is thermodynamic. In 1972, Jacob Bekenstein argued that black holes must have entropy, a measure of disorder, or of the number of microstates compatible with the macroscopic description of the system. His argument was indirect but compelling. The laws of thermodynamics prohibit the total entropy of a closed system from decreasing. If black holes had no entropy, an observer could reduce the total entropy of the universe by throwing high-entropy objects into a black hole and having them disappear behind the event horizon, never to contribute to the universe's entropy accounting again. This would violate the second law of thermodynamics, one of the most robust principles in all of physics. Therefore, black holes must have entropy, and that entropy must increase whenever something falls in. Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon, the spherical surface beyond which nothing can escape. This was a radical proposal for two reasons. First, entropy is normally thought of as a property of the volume of a system, reflecting the number of ways its internal degrees of freedom can be arranged. Entropy proportional to area rather than volume suggests that the relevant degrees of freedom are concentrated on the surface rather than distributed through the interior. Second, the fact that entropy increases when things fall in, while the event horizon area also increases when things fall in, required a specific relationship between the two that Bekenstein quantified through what we now call the Bekenstein-Hawking entropy formula. Stephen Hawking initially resisted Bekenstein's proposal, partly on the grounds that entropy requires temperature, and a classical black hole has no temperature because nothing can escape from it to carry thermal radiation away. But in 1974, Hawking performed a quantum field theory calculation in curved spacetime and discovered that black holes do radiate thermally. When quantum effects are properly accounted for, the black hole horizon is not a perfect absorber. The quantum vacuum near the horizon is not empty, but filled with virtual pairs of particles and antiparticles constantly appearing and annihilating. Near the horizon, tidal forces can separate a virtual pair before it annihilates, allowing one member to fall into the black hole while the other escapes to infinity. The escaping particle carries energy away from the black hole, and the black hole slowly loses mass through this process. The spectrum of the escaping radiation is thermal, exactly like the radiation from a hot object, with a temperature inversely proportional to the mass of the black hole. Hawking radiation confirmed that black holes are thermodynamic objects with genuine entropy and genuine temperature, not metaphorical ones. This was a major step forward, but it immediately created a new and deeper problem, the information paradox. If a black hole radiates thermally and eventually evaporates completely, what happens to the information that described the matter that fell in? In ordinary thermodynamics and in quantum mechanics, information is conserved. The quantum state of a system evolves unitarily, meaning the complete information content of the system at one time determines its complete information content at all other times. Information can be scrambled but not destroyed. If a pure quantum state falls into a black hole, and the black hole eventually evaporates into thermal radiation, the thermal radiation carries no information about the specific state that fell in. It carries only the black hole's total mass, charge, and angular momentum. The information about the detailed quantum state of the infalling matter appears to have been destroyed in the process, which would violate the fundamental unitarity of quantum mechanical evolution. This is the information paradox, and it sits at the center of theoretical physics as a genuine unsolved problem. The resolution of the information paradox has generated an enormous amount of theoretical work over the decades since Hawking first identified it. The resolution matters not only for black holes in isolation, but for the entire question of how quantum mechanics and gravity relate to each other. If information is truly lost in black hole evaporation, quantum mechanics must be modified in some way to allow non-unitary evolution, which would have consequences throughout physics. If information is preserved, it must be encoded in the Hawking radiation in some subtle way that makes the radiation not truly thermal, but only approximately so. And understanding the encoding mechanism would require understanding quantum gravity at a deep level. One of the most influential approaches to this problem begins with a careful accounting of what the Bekenstein-Hawking entropy formula actually means. The entropy of a black hole is proportional to the area of its event horizon in units of the Planck area, the fundamental area scale set by the combination of Newton's constant, Planck's constant, and the speed of light. The specific coefficient is 1/4. This formula is the most precisely determined result in quantum gravity that we currently possess, derived from both the thermodynamic argument and Hawking's calculation, and it must be explained by any successful theory of quantum gravity. The proportionality of entropy to area rather than volume is what gives the formula its most profound implication. If the entropy of a black hole measures the number of quantum states compatible with its macroscopic description, and if that count is set by the surface area rather than the volume, then the fundamental information content of the black hole is encoded on the two-dimensional surface of the horizon rather than in the three-dimensional interior. The interior degrees of freedom, whatever they are, can be fully described by what happens on the boundary. This is not how we normally think about physical systems. A volume of gas has entropy proportional to the number of molecules it contains, which scales with the volume. A black hole's entropy scales with the area of the surface enclosing it. Something about black holes is different at a fundamental level. Gerard T. Hooft and Leonard Susskind independently developed this observation into a general principle in the early 1990s, proposing what became known as the holographic principle. The holographic principle asserts that the maximum information content of any region of space is proportional to the area of the surface bounding that region, not the volume. The three-dimensional physics of the interior can be completely encoded in a two-dimensional description on the boundary. This is more than a statement about black holes. It is a claim about the structure of physical reality in general. The fundamental degrees of freedom that describe a three-dimensional region of spacetime are not the three-dimensional fields within that region, but the two-dimensional data on its boundary. The holographic principle is not merely a philosophical conjecture. It received a concrete mathematical realization in 1997 when Juan Maldacena discovered what is now called the anti-de Sitter/conformal field theory correspondence, or AD-SCFT. This is a precise mathematical duality between two very different physical theories. On one side is a theory of gravity in a specific type of curved spacetime, anti-de Sitter space, which has a particular negatively curved geometry. On the other side is a quantum field theory without gravity, defined on the lower dimensional boundary of that spacetime. The duality asserts that these two theories are exactly equivalent. Every physical question that can be asked in the bulk gravitational theory has a corresponding formulation in the boundary field theory, and the answers must agree. Neither theory is more fundamental than the other. They are two descriptions of the same physics. The AD-SCFT correspondence is remarkable for several reasons. It provides a concrete example in which a theory of quantum gravity in a higher dimensional space is exactly equivalent to a quantum field theory without gravity in a lower dimensional space. This means that at least in this specific setting, gravity is not an independent fundamental force in the usual sense. It is dual to a quantum field theory that does not contain gravity, and questions about gravitational physics in the bulk can be translated into questions about non-gravitational physics on the boundary. Gravity emerges from the boundary description rather than being built in as a fundamental ingredient. The correspondence also provides a potential resolution to the information paradox in the AD-SCFT context. If the bulk gravitational theory is exactly dual to a unitary boundary field theory, and if quantum field theories are unitary by construction, then the bulk theory must also be unitary, and information cannot be lost in the process of black hole formation and evaporation. The apparent loss of information in the Hawking radiation must be an artifact of approximations in the bulk description, particularly the approximation of treating the black hole as emitting exactly thermal radiation, while ignoring the subtle quantum correlations that encode the information in the radiation. The boundary theory guarantees unitarity, and the challenge is to understand how the bulk description reproduces that unitarity in detail. This challenge has led to some of the most fascinating recent work in theoretical physics, exploring what are called quantum extremal surfaces, islands, and replica wormholes. These are techniques for calculating the entropy of the Hawking radiation as a function of time in a way that is consistent with unitarity. The results suggest that the entropy of the radiation initially increases as more radiation is emitted, then reaches a maximum, and then decreases as the black hole evaporates, eventually returning to zero when the black hole is completely gone and all the information has been encoded in the radiation. This behavior, known as the Page curve after physicist Don Page, who predicted it on general grounds in the 1990s, is exactly what unitarity requires. Reproducing it from detailed calculations in the gravitational theory has required discovering that the dominant contribution to the gravitational path integral at late times comes from configurations, the islands and replica wormholes, that are not visible in the semi-classical approximation, but become important precisely when information recovery is relevant. The resolution of the information paradox through these methods, while not complete, has been taken as strong evidence that the holographic principle is correct and that gravity is genuinely emergent from a more fundamental description. If that is true, the implications extend well beyond black hole physics. If the gravitational dynamics of spacetime are determined by the information content of boundaries rather than by local fields in the bulk, then the structure of spacetime itself is a derived concept rather than a fundamental one. Spacetime geometry, including its curvature and its causal structure, would emerge from the quantum information structure of the boundary theory in a way that is not yet fully understood, but that is clearly non-trivial. This idea of emergent spacetime connects to another line of theoretical work that has developed over the same period, the connection between quantum entanglement and the geometry of spacetime. Entanglement is a purely quantum mechanical phenomenon where two systems in a joint quantum state have correlations that cannot be attributed to any classical shared properties. The entanglement between two subsystems is measured by the entanglement entropy, a quantity that satisfies mathematical relations similar to those satisfied by geometric areas in curved spacetime. In 2006, Shinsei Ryu and Tadashi Takanagi discovered a precise formula in AD-SCFT relating the entanglement entropy of a region of the boundary field theory to the area of a specific surface in the bulk gravitational theory, the minimal surface in the bulk, whose boundary coincides with the boundary of the region on the boundary. The Ryu-Takanagi formula is an extension of the Bekenstein-Hawking formula to more general situations, and it makes a striking claim. The geometric area of surfaces in the bulk gravitational theory is determined by the quantum entanglement structure of the boundary theory. Geometry is entanglement. The curvature and connectivity of the bulk spacetime reflect the pattern of quantum correlations in the boundary quantum theory. This connection has been elaborated and extended in many subsequent papers, developing into a picture where the very connectivity of spacetime, the fact that different regions of space are close to or far from each other, is determined by the entanglement between the corresponding boundary degrees of freedom. If two regions of the boundary theory are highly entangled, the corresponding bulk regions are connected by a short geometric path. If the entanglement between boundary regions is reduced, the bulk geometry changes and the corresponding regions become more distant or even disconnected. The extreme case of this principle, where entanglement is completely severed between two parts of the boundary system, corresponds to the bulk geometry splitting into two disconnected spacetimes. The slogan that has emerged from this line of work is ER equals EPR, proposed by Maldacena and Susskind in 2013. ER refers to the Einstein-Rosen bridge, also known as a wormhole, which is a solution of general relativity that connects two separate regions of spacetime through a geometric throat. EPR refers to the Einstein-Podolsky-Rosen pairs of entangled particles, the maximally entangled quantum systems that Einstein, Podolsky, and Rosen used in their famous 1935 paper to argue for the incompleteness of quantum mechanics. The ER equals EPR conjecture asserts that any pair of maximally entangled particles is connected by a microscopic wormhole, and more generally that entanglement and geometric connectivity are the same thing expressed in two different languages. If this is right, then the connectivity of spacetime is not a given. It is a consequence of the quantum entanglement structure of the underlying degrees of freedom, whatever those degrees of freedom turn out to be. Adding entanglement creates geometric connections, removing it disconnects spacetime. The geometry of the universe is written in the language of quantum information, not in the language of fields and forces as we normally think of it. Spacetime is not the stage on which quantum mechanics is performed. Spacetime is what quantum mechanics produces when the information structure has a particular form. These ideas, while developed primarily in the mathematical context of AD-SCFT, are meant to be more general. The specific setting of anti-de Sitter spacetime and conformal field theory is a controlled laboratory where calculations are possible, but the underlying physics is expected to apply in other settings as well, including the de Sitter spacetime that describes our accelerating universe and the flat spacetime of ordinary experience. Extending the holographic framework from anti-de Sitter to de Sitter spacetime is one of the major challenges in theoretical physics, and it is relevant precisely because we live in a universe that is accelerating toward a de Sitter-like fate rather than the anti-de Sitter geometry, where the framework is best understood. The challenge of de Sitter holography connects back to the cosmological tensions we discussed earlier in a specific way. Anti-de Sitter space has a boundary, a well-defined conformal boundary at spatial infinity, where the boundary quantum field theory lives. De Sitter space, the geometry that describes a universe dominated by a cosmological constant, does not have a boundary at spatial infinity in the same sense. Instead, it has a cosmological horizon, a surface beyond which any given observer cannot see, analogous to the event horizon of a black hole, but extending in all directions around the observer. The holographic description of de Sitter space is expected to involve degrees of freedom associated with this cosmological horizon rather than a spatial boundary at infinity, but the precise formulation remains elusive. The fact that de Sitter holography is difficult is not merely a technical obstacle. It may reflect something fundamental about the nature of dark energy and the cosmological constant. If the cosmological constant is the energy density of a stable de Sitter vacuum, then the holographic description of our universe involves a finite number of degrees of freedom, set by the area of the cosmological horizon in Planck units. A finite number of degrees of freedom means a finite Hilbert space, the mathematical space of quantum states, and that has implications for the long-term behavior of the universe that are not fully worked out. It may mean that the universe cannot remain in a de Sitter phase indefinitely, that it must eventually tunnel into a different vacuum state, or that the de Sitter description breaks down at some point. These considerations have motivated theoretical proposals that dark energy may not be a true cosmological constant, but a metastable configuration that will eventually decay, releasing the energy stored in the false vacuum and transitioning the universe to a different state. In the landscape of string theory, there are potentially an enormous number of metastable vacuum states with different values of the effective cosmological constant, and the universe might be in one of them rather than in the true ground state. The timescale for decay from a metastable vacuum is typically exponentially long compared to any timescale relevant to current cosmology, but if it is finite, the possibility of a future vacuum decay adds another dimension to the great filter question. A vacuum decay event would propagate as a bubble of new vacuum expanding at the speed of light. Inside the bubble, the laws of physics would be different, with different values of the fundamental constants. Outside the bubble, the old physics would persist until the bubble wall arrived. A civilization with any advance warning of a bubble nucleation event in its vicinity would have no defense against it, because the bubble wall travels at the speed of light and cannot be detected before it arrives. The information about the nucleation event would be traveling with the bubble wall rather than ahead of it. This is the most absolute version of a filter, instantaneous, universal, and unpreventable. The probability of vacuum decay is extremely sensitive to the details of the potential landscape of the underlying fundamental theory, and current theoretical estimates span an enormous range depending on assumptions about the landscape's structure. The observational constraints on vacuum decay come from the fact that we exist. If the universe had decayed to a different vacuum in our past light cone, we would not be here to ask the question. This anthropic constraint limits the decay rate in our past, but does not bound the decay rate in our future with equal rigor. The great filter in this interpretation is a cosmological phenomenon rather than a biological or technological one, and it operates through quantum tunneling rather than through any challenge that intelligence or technology might in principle address. Returning to the holographic framework, the connection to the cosmological anomalies we have been discussing is not yet a direct one. The holographic principle, add SCFT, and emergent spacetime are theoretical ideas that are well developed in specific mathematical settings, but have not yet produced quantitative predictions that could directly explain the Hubble tension or the early galaxy anomalies. The connection is more structural. If spacetime and gravity are emergent from a more fundamental description, then the effective theories we use to describe cosmology, including lambda CDM and general relativity at cosmological scales, are approximations to that deeper description. Approximations have regimes of validity, and outside those regimes they fail. The question is whether the cosmological anomalies are evidence that we are pushing outside the regime of validity of the effective description. This possibility is taken seriously by a growing number of theorists who are exploring what might be called quantum gravitational corrections to cosmology. If the standard cosmological model is an effective theory derived from a deeper holographic description, corrections to the effective theory from the underlying quantum structure would be expected to become relevant at specific scales or epochs. The most natural scale for such corrections is the Planck scale, which is extremely small, but coherent effects involving the Planck scale can become relevant on cosmological scales in specific circumstances, particularly when the universe is near a de Sitter configuration, where the cosmological horizon is well defined, and the holographic description is most relevant. One specific proposal along these lines involves what is sometimes called the swampland program in string theory. The swampland is the region of the landscape of possible effective field theories that cannot be consistently completed into a theory of quantum gravity. The claim is that de Sitter space with a positive cosmological constant is in the swampland, that a stable de Sitter vacuum cannot be consistently realized in string theory. If this is correct, dark energy cannot be a true cosmological constant. It must be dynamical, and the equation of state must be evolving away from -1. This would be exactly the signal that Dacey is finding hints of, a dark energy that is not constant but evolving, precisely because a true constant is theoretically forbidden. The swampland conjecture is controversial within the string theory community, and the evidence for or against it comes from complex mathematical calculations in the landscape rather than from observation. But if it is correct, the daisy hints of dark energy evolution are not merely an observational curiosity. They are a reflection of the underlying structure of quantum gravity, a sign that the universe is navigating through a potential landscape rather than sitting in a stable vacuum. The cosmological constant is not constant because it cannot be constant in any consistent theory of quantum gravity, and the parameter we have been calling lambda, the fixed background energy, is actually a slowly rolling field that will eventually decay or settle into a different configuration. This brings the argument full circle back to the fine-tuning problem. If the cosmological constant is not constant but dynamical, the fine-tuning problem transforms from the question of why a fixed parameter has an extraordinarily small value to the question of why a dynamical field is currently near a very flat part of its potential, producing what looks like near-constant vacuum energy on cosmological timescales. The problem does not disappear, but it changes character. A dynamical explanation for the small value of dark energy might be possible through a mechanism that drives the field towards small values over time, similar to how the inflated field was driven towards small values during inflation by the expansion of the universe. Such a mechanism would not require the extraordinary cancellation between quantum corrections that makes the cosmological constant problem so difficult in the static picture. The ideas we have been discussing in this chapter are connected by a common theme that recurs throughout the most ambitious current work in theoretical physics. What we perceive as fundamental may be emergent, and the deepest level of reality may be organized around principles that look very different from the field theories and geometries we use in our current description. Spacetime is potentially emergent from quantum entanglement. Gravity is potentially emergent from the thermodynamics of information on boundaries. The cosmological constant is potentially a dynamical field rather than a true constant. The distinction between the bulk and the boundary, between the physics inside a region and the information on its surface, may be the most fundamental distinction in the structure of reality. If any of these ideas are correct, the cosmological anomalies we have cataloged, the early galaxy tensions, the Hubble disagreement, the dark energy evolution hints, might not be independent problems requiring independent solutions. They might be different manifestations of the same underlying departure from the effective description, different places where the approximation of treating spacetime and gravity as fundamental rather than emergent begins to break down. The corrections from the deeper description would not appear as large, dramatic failures of the model, but as small, systematic biases in the predictions, exactly the kind of percent-level discrepancies that characterize the current tensions. This is speculative but not irresponsible. The history of theoretical physics is full of cases where apparently unrelated anomalies were unified by a deeper framework that revealed their common origin. The photoelectric effect, blackbody radiation, and the stability of atoms were disparate puzzles in the late 19th and early 20th centuries, each with its own proposed ad hoc explanation. Quantum mechanics revealed them as manifestations of the same underlying quantization principle. The failure of Newtonian mechanics for fast-moving objects, the Michelson-Morley null result, and the electrodynamic behavior of moving charges were separate puzzles before special relativity revealed them as aspects of the same spacetime structure. The current cosmological anomalies may be waiting for a similar unifying insight, one that is not yet available because the theoretical framework that would make the connection is still under construction. The great filter, viewed through the lens of everything we have discussed, takes on additional dimensions that were not visible at the beginning. We started with the marathon metaphor, the crowded mile 5, the deceptive calm of early success, and the hidden bottleneck that most trajectories do not survive. That framework was initially applied to the biological and civilizational question of why the cosmos appears silent despite the abundance of potentially habitable worlds. But the cosmological journey we have taken reveals that the filter concept operates at multiple levels of physical reality simultaneously. At the most fundamental level, the fine-tuning of physical constants represents a filter at the level of universes. Most configurations of fundamental physics do not permit the complexity required for life to emerge. Our universe sits in the narrow region that does, but that selection carries no implications for subsequent filters that operate within our universe on shorter timescales. Surviving the fine-tuning filter is a prerequisite for existence, but not a guarantee of continuity. At the next level, the dynamics of cosmic structure formation represent a filter at the level of environments. The growth of large-scale structure, the formation of galaxies, the synthesis of heavy elements in stellar interiors, the delivery of those elements to planetary surfaces, and the long-term stability of planetary environments all depend on the cosmological parameters being configured in ways that permit each step. If the Hubble tension reflects a genuine incompleteness in our understanding of the expansion history, the catalog of environments that meet all these requirements may be different from what we currently estimate. Some environments that we classify as potentially habitable may face additional constraints from the dynamical behavior of dark energy or from the quantum gravitational corrections to the effective cosmological description. At the civilizational level, the filter question remains as open as it was at the beginning. The cosmological anomalies we have discussed do not directly answer whether civilizations like ours tend to survive technological development or tend to destroy themselves or face some other obstacle. But they do affect the framework within which we estimate the prevalence and distribution of civilizations across cosmic time and space. If dark energy is evolving, the long-term fate of the universe is less certain than we assumed. If the cosmological constant is dynamical, the possibility of a future vacuum decay is more physically grounded than in a static picture. If spacetime is emergent, the stability of the physical laws on which civilization depends may be less absolute than we have assumed. None of these are imminent threats on human timescales. The evolution of dark energy, if real, is happening on timescales of billions of years. The probability of vacuum decay in our vicinity over the next billion years is, under any reasonable estimate, negligibly small. The emergence of spacetime from quantum information does not mean that spacetime is unstable on accessible timescales. But these considerations matter for the great filter question, because the filter is a question about the entire distribution of outcomes for civilizations, not just about the near-term future of any single civilization. If the physics allows for processes that eliminate civilizations or their environments on timescales of billions of years, those processes can contribute to the filter even if they are irrelevant to any individual civilization's immediate concerns. The more relevant near-term implication of the cosmological tensions is epistemic rather than physical. If our best model of the universe is incomplete in ways that current instruments are beginning to reveal, then our confidence in our understanding of what is physically possible and physically stable is lower than we thought. The margins of error on our forecasts about long-term physical conditions are larger than we assumed. The space of possible futures that are consistent with current observations is wider than the standard model implies. That wider space includes some futures that are more hospitable to long-term civilization survival and some that are less hospitable, and we currently cannot determine which portion of the space is more densely populated. This epistemic humility is not defeatism. It is the appropriate scientific response to data that is ahead of theory. When the instruments find patterns that the models do not predict, the honest response is to widen the error bars on everything that depended on the models being correct, while simultaneously working to build better models that explain the new patterns. The wider error bars are not a failure of cosmology. They are evidence that cosmology is working, finding the limits of its current description and pressing for a more complete one. The comparison to earlier scientific revolutions is instructive here, not as a guarantee that a revolution is coming, but as a reminder of what revolutions look like from the inside. Before special relativity, the failure of Michelson and Morley to detect the luminiferous ether looked like a measurement problem. The instruments were good. The result was clean. The existing theory predicted a specific signal and got none. For years, physicists tried to explain the null result within the existing framework, invoking length contraction and time dilation as ad hoc mechanisms. Einstein recognized that the null result was not a measurement problem but a fundamental clue. The speed of light is the same for all observers because the structure of spacetime demands it, and the ad hoc mechanisms were symptoms of a deeper principle. The cosmological tensions may occupy a similar position. Each individual tension can be addressed within the existing framework through some combination of revised systematics and ad hoc modifications. But the ensemble of tensions, pointing in related directions across independent methods and independent physical domains, may be symptom of a deeper principle that the existing framework cannot accommodate. The deeper principle, if it exists, might resolve multiple tensions simultaneously by revealing why the effective description produces the specific biases that look like discrepancies. That would be the cosmological equivalent of recognizing that length contraction and time dilation are not ad hoc fixes, but consequences of Lorentz symmetry. What would such a deeper principle look like? This is where honest scientific humility requires admitting that we do not know. The theoretical frameworks we have discussed, holography, emergent gravity, quantum entanglement as geometry, swampland constraints, are all proposals for what the deeper description might look like. They make some testable predictions, and those predictions are being tested with current and planned experiments. But none of them has yet made a prediction that is both distinctive and confirmed, the signature of a successful theoretical revolution. The work of building that framework is ongoing, and its outcome is genuinely uncertain. What we can say is that the question is being asked with more rigor and better tools than ever before. The theoretical frameworks are more sophisticated. The observational instruments are more sensitive. The computational resources for comparing theoretical predictions to data are vastly more powerful. The community of researchers engaged with these questions is larger and more internationally diverse. The speed at which ideas are shared and tested has accelerated dramatically. If a deeper framework exists and is findable with human tools and human timescales, the current era may be the one in which it begins to come into view. The most honest thing that can be said about where all of this leaves us is that we are at a moment of productive uncertainty. The standard cosmological model has achieved genuine successes that should not be dismissed or minimized. It explains an enormous range of observations with remarkable precision and internal consistency. The cosmic microwave background, the large-scale structure of the universe, the expansion history as traced by supernovae, the abundance of light elements, and the statistical properties of galaxy clustering all fit within a single framework parameterized by a handful of numbers. That is a genuine intellectual achievement, earned over decades of careful work by thousands of researchers. At the same time, the same precision that allowed the model's successes is now allowing its tensions to be quantified clearly enough to prevent comfortable dismissal. The Hubble tension at 5 sigma is not a rumor. The early galaxy anomalies that persist after spectroscopic revision are not one anomalous object. The daisy hints of evolving dark energy are not a single paper's result, but a pattern emerging from millions of spectra across a wide redshift range. The S8 tension in large-scale structure clustering is not confined to one survey's peculiarity. These are independent lines of evidence, each methodologically distinct, each crossing different systematic risks, each pointing in directions that are at least partially consistent with each other and partially inconsistent with the simplest version of the standard model. The scientific response to this situation is neither panic nor dismissal. It is continued measurement, continued theoretical exploration, and continued willingness to revise the framework when the evidence demands it. The pace of that revision will be set by the data, as it always is in empirical science. The next generation of surveys and instruments will either confirm the patterns currently emerging or reveal them as systematic artifacts. Either outcome advances understanding. Confirmed patterns demand new theory. Dissolved artifacts reveal the limits of current measurement methods and point toward better techniques. The Vera Rubin Observatory, now beginning its legacy survey of space and time, will map billions of galaxies with weak gravitational lensing and photometric redshifts, providing a massive new constraint on the S8 tension and the growth of large-scale structure. The Euclid satellite will survey the galaxy distribution and weak lensing signal across a significant fraction of the extragalactic sky with spectroscopic and photometric instruments, providing bow and lensing constraints with different systematic errors than ground-based surveys. The Nancy Grace Roman Space Telescope will observe supernovae and conduct a wide-area near-infrared survey with capabilities complementary to Webb. The Simons Observatory and CMB-S4 will push the measurement of the cosmic microwave background to much higher sensitivity and angular resolution, constraining neutrino masses, inflationary gravitational waves, and the fine details of the damping tail that encode information about the early universe's particle content. Each of these instruments will generate data that is both confirmatory and exploratory, confirming or refuting the current anomalies, while opening new windows on aspects of the universe that have not yet been precisely characterized. The combination of all these new data sets with each other, and with the Webb results and DAISY results, will produce a picture of the universe that is far more detailed and far more constraining than anything currently available. If the tensions are real, they will become more statistically significant and more coherent. If they are artifacts, they will dissolve as the independent instruments disagree with the biased measurements. The great filter throughout all of this remains where it has always been. In the future, unknown, possibly close, possibly distant, possibly surmountable, possibly not. The cosmological investigation we have undertaken does not resolve the filter question, but it changes the context in which the question must be asked. A civilization whose cosmological model is under pressure in several places, simultaneously, is in a different epistemic position than a civilization whose model is secure and well-tested across all domains. The former has reasons to be less confident in its long-term forecasts, not because catastrophe is imminent, but because the framework on which those forecasts rest is known to be incomplete in ways that are not yet fully characterized. That incompleteness is not an argument for despair. It is an argument for continued investigation, continued refinement of the tools we use to understand our situation, and continued humility about the limits of what we currently know. The universe appears to be stranger than our best model. That strangeness, if it is confirmed, is an invitation to understand it more deeply. The history of physics suggests that deeper understanding, when it comes, tends to reveal not a more dangerous or hostile reality, but a more complex and more beautiful one, with new structures and new principles that reframe the questions we thought we were answering. The silence of the cosmos may reflect a filter that most civilizations do not survive. Or it may reflect the limits of our search methods and the finite time that civilization has existed with sensitive instruments. Or it may reflect the vast distances and timescales of cosmic communication that make contact improbable on human timescales, even if civilizations are common. The cosmological investigations we have been following do not distinguish between these possibilities. But they do suggest that the universe is configured in a way that is more dynamic, more subtly balanced, and less fully understood than we assumed even a decade ago. That configuration may be compatible with the existence of many civilizations across cosmic history. Or it may be telling us something about why the distribution of outcomes is more concentrated at the beginning of the marathon and thinner toward the finish than our naive expectations would suggest. We are at mile 5. The crowd is real. The finish line is beyond the visible horizon, and the mile markers have begun to wobble in ways that the map did not predict. Whether that wobble is the first warning of the decisive filter or simply a more complex terrain than we expected, we cannot yet say. What we can say is that the instruments to understand it are being built, the measurements are being made, and the physics is being worked through with the rigor and honesty that the question deserves. That is the best we can do, and it is not nothing. In the long run, it may be everything. There is a final thread worth following before we close, and it concerns the relationship between the cosmic and the personal, between the scale of these investigations and the timescale of a human life or a human civilization. The questions we have been exploring operate on scales of billions of light years and billions of years. The tensions in the cosmological model, even if they point toward genuinely new physics, will take decades to resolve through the accumulation of better measurements and the development of better theories. The great filter, if it exists and is ahead of us, may not become relevant on timescales shorter than centuries or millennia. Why should any of this matter to us now, in this moment, with the current instruments and the current knowledge? The answer is that the way we understand our situation shapes the decisions we make about it, even when the timeline is longer than any individual lifetime. A civilization that believes its cosmological model is settled and its long-term physical situation is secure will make different investments in research and preparation than a civilization that recognizes the foundations of that model are under active revision. A civilization that takes seriously the great filter question, at whatever level it operates, will approach technological development with different levels of caution than one that assumes the long-term survival of complex civilization is guaranteed by the trajectory of progress. The cosmological tensions we have discussed are not doomsday signals. They are not evidence that the universe is hostile or that civilization is doomed or that the filter is close and impassable. They are evidence that our understanding of the universe is incomplete and that the parameters of our long-term situation are less precisely known than we assumed. That evidence calls for more investigation, not less. It calls for more precise instruments, more creative theoretical proposals, and more honest assessment of what we know and what we do not. It calls for exactly the kind of scientific work that Webb and Dacey and the next generation of surveys represent, the patient, systematic, careful accumulation of better information about the universe we inhabit. The marathon metaphor has carried us this far, and it deserves a final use. At mile 5, surrounded by the crowd, with the finish line invisible and the map's reliability in question, the appropriate response is not to stop running. It is to pay more careful attention to the terrain, to update the map as new information arrives, to watch the runners ahead for signs of what the course demands, and to be honest about not knowing what comes after the next turn. That combination of continued motion, careful observation, and epistemic honesty is what the cosmological moment requires of us. James Webb did not catch the universe lying exactly. It caught us assuming things that may not be true. The universe was never lying. It was always there, doing what it does, indifferent to our models. We were the ones who built the models and treated them as final, who extrapolated beyond the evidence and called the extrapolation certainty. Webb gave us the means to notice the discrepancy. That is not a failure, that is the system working. The universe has always been stranger than we thought, and every time we build an instrument sensitive enough to see the strangeness, we get closer to understanding it. The race continues. The crowd is real. The terrain is more complex than the map suggested. And the instruments to understand it better are, right now, looking at the sky. Every measurement we have discussed so far lives inside a framework that most working scientists treat as given. The framework of continuous spacetime, of fields propagating through a smooth geometric background, of gravity as the curvature of that background produced by the distribution of energy and momentum within it. General relativity is the mathematical expression of that framework, and it has passed every experimental test ever devised for it with extraordinary precision. From the precession of Mercury's orbit to the bending of light around the Sun, from the slowing of clocks in gravitational fields to the detection of gravitational waves from merging black holes a billion light-years away, general relativity has been confirmed so thoroughly and across such a wide range of scales that questioning it feels almost impertinent. Yet the cosmological tensions we have been tracing suggest that something is incomplete, and if the incompleteness is not in our measurements alone, it must be somewhere in the theoretical scaffolding. The question of where exactly requires us to look more carefully at the structure of general relativity itself, not as a finished edifice, but as an effective description that may be pointing beyond itself. General relativity emerged from Einstein's attempt to extend special relativity to include gravitational effects. The conceptual leap was recognizing that gravity is not a force in the conventional sense, but a manifestation of the curvature of spacetime. Matter and energy curve spacetime, and curved spacetime tells matter and energy how to move. The feedback between these two processes, encoded in Einstein's field equations, produces the full range of gravitational phenomena from the mundane to the extreme. The equations are deceptively compact but mathematically rich, generating solutions that range from the gentle curvature around the Earth to the violent singularities at the centers of black holes to the cosmological solutions that describe the expansion of the entire universe. What general relativity does not include is quantum mechanics. This is not an oversight. Einstein was aware of the incompatibility between his theory and the quantum mechanics that was being developed in parallel during the same decades. Quantum mechanics describes the behavior of matter and energy at small scales in terms of probability amplitudes, discrete energy levels, and the superposition of states. General relativity describes the geometry of spacetime in terms of smooth continuous fields. Combining the two frameworks in a mathematically consistent way has proven to be one of the hardest problems in theoretical physics, resisting solution for nearly a century. The incompatibility is not merely technical, it is conceptual. In quantum mechanics, the state of a system is described by a wave function that assigns probability amplitudes to different outcomes of measurements. The wave function evolves according to the Schrödinger equation, which is linear. The superposition of two valid states is also a valid state. In general relativity, the geometry of spacetime is determined by the stress-energy tensor, the distribution of matter and energy, through a set of nonlinear equations. If matter can be in a quantum superposition of different configurations, the spacetime it produces should also be in a superposition of different geometries, but the meaning of a superposition of geometries is not straightforwardly defined within either framework. Attempts to quantize gravity directly, by applying the same procedure that worked for the other fundamental forces, run into divergences that cannot be removed through the renormalization techniques that work for quantum electrodynamics and the other quantum field theories of the standard model of particle physics. The naive quantization of general relativity is non-renormalizable, meaning that infinitely many free parameters would be required to absorb the divergences, removing all predictive power. This signals not that gravity cannot be quantized, but that general relativity is not the right starting point for a quantum theory of gravity. It is an effective theory, valid at low energies and large distances, but breaking down at the Planck scale where quantum gravitational effects become strong. The search for a consistent theory of quantum gravity has motivated the development of string theory, loop quantum gravity, causal dynamical triangulations, and other approaches. Each approach has genuine insights and genuine difficulties. String theory provides a consistent framework for quantum gravity in certain dimensions and backgrounds, unifies gravity with the other forces in a natural way, and has given rise to add SCFT and the holographic insights we discussed in the previous chapter. But it has not yet produced a definitive prediction that has been confirmed by experiment, and the landscape of possible string theory vacua is so large that connecting the theory to specific observations remains an unsolved challenge. Loop quantum gravity provides a background-independent quantization of the geometric degrees of freedom of spacetime, suggesting that space itself has a discrete structure at the Planck scale, but it has difficulty incorporating the matter content of the standard model of particle physics in a natural way, and has not yet made confirmed observational predictions. The situation is one that physicists are accustomed to in the history of science, but find uncomfortable to inhabit. A regime where the existing theories are known to be incomplete, the directions for extension are partially charted but not definitively settled, and the observational data that could discriminate between competing proposals is difficult to obtain because the relevant scales are far beyond the reach of current experiments. The Planck scale, where quantum gravity effects are expected to be strong, corresponds to energies that are 15 orders of magnitude beyond what the Large Hadron Collider can access. Direct probes of quantum gravity physics are therefore not available in the conventional experimental sense, and progress must come from theoretical coherence, indirect observational signatures, and the kind of consistency arguments that allowed the development of quantum mechanics in the absence of direct access to atomic-scale processes. This is precisely why the cosmological anomalies we have been discussing carry special significance. They represent one of the few observational domains where quantum gravitational effects might plausibly leave indirect signatures at accessible scales. The early universe, the structure of black holes, and the behavior of dark energy are the places where the effective theory of gravity as general relativity plus quantum field theory is most likely to receive corrections from the deeper quantum gravitational description. And they are also the places where the current tensions in the standard cosmological model are most visible. The holographic principle, which we introduced in the context of black hole thermodynamics, becomes relevant here as a potential guide to what the deeper description looks like. If the information content of any region of space is bounded by the area of its boundary surface rather than its volume, this imposes constraints on the effective field theories that can describe physics in that region. Field theories in their conventional formulation allow an unbounded number of degrees of freedom in any finite volume, because fields can vary independently at each point of a continuous space. Holographic constraints say that the actual number of independent degrees of freedom is finite and set by the boundary area. This discrepancy between the degrees of freedom assumed by conventional field theory and those actually available in a holographic description is one way to understand the cosmological constant problem. The conventional field theory calculation assumes far more degrees of freedom than the holographic description allows, and the discrepancy between the two calculations is precisely what shows up as the enormous apparent vacuum energy. The holographic entropy bound, first formulated by Raphael Bauso in the late 1990s, extends the Bekenstein-Hawking entropy to a general statement about the information content of light sheets, the surfaces swept out by light rays emanating from a region of space. Bauso's covariant entropy bound says that the entropy passing through a light sheet cannot exceed the area of the initial surface divided by 4 times Newton's constant in Planck units. This bound has been tested in many specific contexts and has never been violated, suggesting that it is a genuine constraint on the physics of any consistent theory of quantum gravity rather than a property specific to black holes. Universality of the entropy bound has motivated attempts to reconstruct the laws of gravity as consequences of thermodynamic principles applied to the boundaries of causal regions. Ted Jacobson showed in 1995 that the Einstein field equations of general relativity can be derived by applying the first law of thermodynamics to the Rindler horizons of accelerating observers, the causal boundaries that separate accelerating observers from regions of spacetime they cannot access. The derivation treats the area of the horizon as entropy and the energy flux through the horizon as heat, and requires that the entropy-area relationship be satisfied for every local Rindler horizon in spacetime. The result is that the Einstein equations are equivalent to thermodynamic equilibrium conditions on these surfaces. Gravity, in this derivation, is not a fundamental force, but a thermodynamic effect, arising from the entropy of the microscopic degrees of freedom living on causal boundaries. Eric Verland extended this idea in 2010 with a proposal for emergent gravity in which the gravitational force is an entropic force, arising from the tendency of systems to increase entropy. In Verland's framework, gravity between two masses appears because the entropy of the holographic screen between them would increase if the masses were closer together, and the entropic force drives them toward the higher entropy configuration, which is the configuration where they are closer. This is analogous to the way that the tension in a stretched polymer arises not from any fundamental force, but from the tendency of the polymer to increase its configurational entropy by coiling into a more compact state. The macroscopic force is real and measurable, but its origin is statistical rather than fundamental. Verlin's emergent gravity proposal is more speculative than Jacobson's derivation, and it has been criticized on several grounds. The entropic force argument works well for Newtonian gravity at the level of a heuristic derivation, but faces difficulties when extended to the full relativistic theory. It has also been argued to make predictions for the distribution of dark matter in galaxies that may conflict with observations, though this claim is debated and depends on specific implementation choices. The proposal remains an active area of investigation rather than an established result. But its significance as a conceptual provocation is genuine. It asks whether the entire framework of gravity as a force, or as spacetime curvature, might be replaced by a description in terms of information and entropy, with the gravitational phenomena we observe being the macroscopic manifestation of microscopic information processing on holographic surfaces. The question of whether gravity is emergent or fundamental matters for cosmology in a specific way. If gravity is an effective description that arises from more fundamental degrees of freedom, the cosmological constant is not a parameter of the fundamental theory. It is a property of the effective description, and its value is determined by the properties of the underlying microscopic theory rather than being a free parameter that must be fine-tuned. The enormous discrepancy between the quantum field theory prediction and the observed value might then be not a fine-tuning problem requiring cancellation between large terms, but a consequence of the mismatch between the degrees of freedom assumed by quantum field theory and those actually present in the holographic description. The vacuum energy calculation in quantum field theory is wrong not because the terms fail to cancel, but because the calculation is using the wrong framework, one that assumes more degrees of freedom than actually exist. This is a genuinely attractive possibility because it would resolve the cosmological constant problem in a structurally clean way rather than through a precise cancellation. But it requires the underlying holographic framework to be developed to the point where it makes specific quantitative predictions that can be tested. The holographic framework is well developed in the anti-de Sitter context through AD-SCFT, but our universe is not anti-de Sitter. Extending the framework to de Sitter spacetime, or to the more general cosmological setting that describes our universe, remains an open problem that many theorists are actively working on. The difficulty of de Sitter holography is not purely technical. It reflects a deep conceptual difference between the two types of spacetime. Anti-de Sitter space has a conformal boundary at infinity where a well-defined field theory can be placed, and the AD-SCFT correspondence gives a precise dictionary between bulk gravitational observables and boundary field theory observables. De Sitter space has no spatial boundary at infinity. Instead, it has a cosmological horizon whose properties depend on the observer. In an accelerating universe, each observer is surrounded by a cosmological horizon beyond which they cannot receive information. This horizon is analogous to a black hole horizon, and by Bekenstein-Hawking reasoning, it should have entropy proportional to its area. But unlike a black hole horizon, the cosmological horizon is observer-dependent, and the entropy associated with it reflects the limitations of any particular observer rather than a property of the geometry itself. Some proposals for de Sitter holography place the holographic degrees of freedom on the future boundary of the de Sitter spacetime, a space-like surface that all light rays eventually reach in the infinite future. This static patch holography or future boundary holography differs from AD-SCFT in fundamental ways, and the corresponding boundary theory is not well understood. Other proposals suggest that de Sitter space is inherently metastable and will eventually decay to a lower energy vacuum, in which case de Sitter holography is not well defined in the strict sense because the spacetime does not persist indefinitely. The swampland conjecture that we mentioned earlier takes this view seriously, asserting that stable de Sitter vacua cannot exist in consistent quantum gravity, and that our universe is therefore in a metastable state that will eventually decay. The relationship between the holographic framework and the cosmological anomalies is therefore indirect but potentially deep. If the resolution of the holographic framework for de Sitter spacetime involves a fundamental reconsideration of what the cosmological constant is and why it has its observed value, that resolution might simultaneously change the predicted expansion history in ways that ease the Hubble tension and produce signatures of dark energy evolution that DAISY is beginning to detect. The anomalies might be early glimpses of the de Sitter holographic structure, pressing through the effective description of general relativity plus a cosmological constant. The seams in the quilt of lambda CDM might be visible precisely where the holographic corrections to the effective theory become most significant. This possibility is motivating a program of research that attempts to connect the abstract mathematical framework of holography to concrete cosmological observables. The challenge is that holographic corrections to cosmology are expected to be small in the current epoch, because the universe is large compared to the Planck scale, and the effective theory should be accurate to a good approximation. The corrections would be of order the Planck length divided by the cosmological scale, which is an absurdly small number in conventional units. To produce effects at the percent level, which is the scale of the current cosmological tensions, would require some mechanism for amplifying Planck scale corrections to cosmological scales. Such amplification mechanisms are not without precedent. Inflation itself is a mechanism that amplified quantum fluctuations at the Planck scale to macroscopic density fluctuations that seeded all subsequent structure formation. The precise spectrum of those fluctuations, measured in the CMB, carries information about quantum gravitational physics during inflation, even though the inflationary epoch itself is not directly accessible to observation. Similarly, the late-time holographic corrections to cosmology might be amplified relative to naive expectations if the de Sitter cosmological horizon is the relevant holographic screen, and if the corrections scale with the inverse of the horizon size rather than the inverse of the Planck scale. The cosmological horizon in our current universe has a physical size of roughly 10 billion light-years. The Planck length is roughly 10 to the power of minus 35 meters. The ratio of these scales is approximately 10 to the power of 60, which is still an enormous suppression. But the relationship between the holographic corrections and observable quantities might not be simply proportional to this ratio. In specific holographic frameworks, corrections to the effective dark energy or to the expansion rate can be enhanced by factors that depend on the entropy of the cosmological horizon, which is proportional to the area in Planck units and is therefore an enormously large number. A correction that is small relative to the Planck scale, but enhanced by the cosmological entropy, can produce percent-level effects in observables, precisely the magnitude of the current tensions. This type of reasoning is not yet developed to the point of making specific, quantitatively precise predictions that can be tested against current data. It is a research direction rather than a completed argument. But it illustrates why the cosmological tensions are taken seriously not just as observational puzzles, but as potential theoretical windows, places where the underlying quantum gravitational structure of spacetime might be pressing against the effective description in ways that our instruments are now sensitive enough to detect. The question of what spacetime is made of, at the most fundamental level, is not merely philosophical. It has consequences for every aspect of cosmology, because cosmology is the study of the large-scale structure and history of spacetime itself. If spacetime is emergent from something more fundamental, then cosmological history is not the history of a fixed geometric background evolving in time, but the history of whatever the fundamental degrees of freedom are doing, with the geometric description being an approximation that is valid when those degrees of freedom are in particular configurations, and that breaks down when they are not. The breakdown of the geometric description is expected to occur at the Planck scale of energy and density, as we noted, but there is a second regime where the geometric description might be strained, and that is the regime of very large scales and very long times, the cosmological regime. Just as the effective theory of a material system breaks down both at the scale of individual atoms and at the scale of the entire macroscopic sample if boundary effects become important, the effective theory of gravity might break down both at the Planck scale and at the cosmological scale where holographic effects on the cosmological horizon become significant. This double breakdown at both small and large scales would be a characteristic signature of a holographic theory where information on boundaries controls the bulk physics. In conventional field theories, the description is local, and the behavior at large scales is determined by the average of the local behavior with boundary effects suppressed by the system's size. In holographic theories, the boundary degrees of freedom are always relevant, and their influence on the bulk physics does not simply average away at large scales. The cosmological horizon is always present for every observer in an accelerating universe, and its entropy, which reflects the limited information available to any observer about the global state of the universe, contributes to the effective dynamics in ways that do not vanish as the universe grows large. This is a qualitatively different kind of physics from what field theory in fixed spacetime produces. In conventional cosmology, the expansion of the universe dilutes matter and radiation, but does not affect the laws of physics themselves. The constants remain constant, the equations of motion remain unchanged, and the only effect of the expanding background is through the scale factor that enters the equations. In holographic cosmology, the expansion changes the size of the cosmological horizon, which changes the entropy associated with it, which changes the effective dynamics of dark energy and the expansion rate. The laws of physics in the effective description are not independent of the state of the universe, but respond to it through the holographic relationship between boundary entropy and bulk dynamics. If this picture is correct, it provides a natural explanation for why dark energy appears to be evolving, as Dacey hints suggest. The dark energy density is not a fixed constant, but a dynamical quantity that responds to the changing entropy of the cosmological horizon as the universe expands. As the universe grows, the horizon area increases, the associated entropy increases, and the effective dark energy density responds to this change in a way that could produce the slow drift away from a pure cosmological constant that Dacey is finding. The drift is not random or arbitrary. It is governed by the holographic relationship between the horizon entropy and the bulk dynamics, which in principle could be calculated from the underlying theory if that theory were more fully developed. Similarly, the Hubble tension might reflect a holographic correction to the relationship between the early universe conditions encoded in the CMB and the late-time expansion rate measured locally. If the effective gravitational dynamics at late times include holographic corrections that are absent from the early time description, the standard lambda CDM model that extrapolates from the early to the late universe using the same effective equations throughout would systematically mispredict the late time expansion rate. The mismatch between the CMB inferred and locally measured Hubble constants would then be not a measurement problem, but a theoretical problem. The model is using the wrong equations for one of the two epochs, and the correction comes from the holographic structure of late-time de Sitter spacetime. This is a speculative but coherent theoretical picture, and coherence is important when dealing with frameworks that are not yet fully developed. The picture does not require any new observations to motivate it. It is motivated entirely by the existing tensions in the standard model and by the theoretical developments in holography and emergent gravity that have been progressing independently. The fact that the theoretical motivations and the observational motivations converge on similar themes, the incompleteness of the effective description at cosmological scales, the dynamical character of dark energy, the sensitivity of the expansion history to quantum gravitational corrections, is itself suggestive, though it falls far short of proof. What would constitute more convincing evidence for this picture? Several observational signatures could in principle discriminate between a holographic cosmological model and lambda CDM. The equation of state of dark energy and its evolution are the most direct handles. A holographic model predicts specific patterns of dark energy evolution that depend on the underlying theory, and those patterns should be distinguishable from both a pure cosmological constant and from generic quintessence models if the measurements are precise enough. Dacey's full 10-year program will measure BAO at many redshifts with much greater precision than the current first-year results, and that precision may be sufficient to distinguish between models if the deviations from lambda CDM are at the level currently hinted. The growth of large-scale structure is another discriminator. Holographic corrections to the expansion history would also affect the growth of matter fluctuations, because structure growth depends on the balance between gravitational attraction and the expansion rate. A specific holographic model predicts a specific modification to the growth factor as a function of redshift, and that modification should be consistent with the expansion history modification rather than being independent of it. Current tensions in the S8 parameter, where weak lensing surveys find lower clustering amplitudes than lambda CDM predicts, might be related to holographic corrections to structure growth. A theoretical model that predicts both the expansion history modification and the structure growth modification consistently would be a more compelling case for holographic cosmology than either observation alone. The primordial gravitational wave signal, if detected by next-generation CMB experiments, would provide information about the inflationary epoch that precedes even the CMB photon decoupling era. The spectrum and statistical properties of primordial gravitational waves are sensitive to the physics of inflation, and if inflation involves holographic effects, those effects might leave signatures in the gravitational wave background that differ from the predictions of standard slow-roll inflation. The detection of such signatures would be powerful evidence for quantum gravitational effects during inflation, though interpreting them would require careful comparison with theoretical predictions from specific holographic inflationary models. Direct detection of quantum gravitational effects at accessible energies remains an open dream rather than an imminent prospect. The Planck scale is deeply inaccessible to particle accelerators, and gravitational wave detectors, while impressive in their sensitivity, measure classical gravitational waves rather than quantum gravitational effects. Some theorists have proposed that decoherence experiments with macroscopic quantum systems might eventually probe the quantum nature of gravity by testing whether gravitational interactions produce entanglement between quantum systems in a way that is distinct from classical interactions. These experiments are in early stages of development and face formidable technical challenges, but they represent a conceptually direct approach to testing quantum gravity that does not require access to Planck scale energies. The Hawking radiation of astrophysical black holes is, in principle, a direct quantum gravitational effect, but its temperature is so low for stellar mass and supermassive black holes that it is undetectable against the background of cosmic microwave background radiation. Only black holes with masses comparable to the Planck mass would emit Hawking radiation at temperatures high enough to be detected directly, and such objects, if they exist, would be relics of a very early cosmological epoch or products of extreme particle physics processes. The detection of primordial black holes with Planck-scale masses would be an extraordinary discovery, but the probability of such detection depends on the cosmological conditions during the early universe in ways that are not currently constrained. The most practical near-term tests of quantum gravitational ideas come from the cosmological observations we have been discussing, not because those observations directly access quantum gravity, but because they constrain the effective theory in regimes where quantum gravitational corrections might be significant. The cosmological horizon, dark energy, and the long-term fate of the universe are precisely the domains where the boundary between classical and quantum gravitational physics is most relevant, and where deviations from the purely classical effective description might be largest. The current anomalies in those domains are therefore not merely puzzles for cosmologists, but potential data points for quantum gravitational theorists. There's a perspective on all of this that is worth making explicit because it changes how the anomalies feel to live with. Every successful scientific revolution in history has had a period before the revolution when the anomalies were present but the resolution was not. During that period, practitioners had to make a choice, often an implicit one, about how to interpret what they were seeing. They could treat the anomalies as measurement problems, as consequences of insufficient precision or systematic errors that would eventually be corrected. They could treat them as model problems, as evidence that the current framework was missing something and needed to be extended. Or they could treat them as both, which is usually the wisest position when the evidence is not yet decisive. The choice of interpretation matters not because it changes what the data are, but because it changes where researchers direct their attention. If the cosmological tensions are measurement problems, the priority is to improve the measurements and track down the systematics. If they are model problems, the priority is to develop new theoretical frameworks that might explain the patterns. In practice, both priorities are being pursued simultaneously, and that parallel effort is appropriate. But there is a tendency in mature scientific communities to weight the measurement problem interpretation more heavily than the model problem interpretation, because mature communities have more infrastructure for improving measurements than for building fundamentally new frameworks. The instruments exist, the pipelines exist, the expertise exists. The incentive structure of academic science rewards incremental measurement improvement more reliably than theoretical revolution. This tendency is not irrational. Most anomalies in the history of science have indeed turned out to be measurement problems rather than model problems, and the prior probability of a measurement error is almost always higher than the prior probability of a fundamental theoretical failure for any given anomaly. But the ensemble of anomalies we have been discussing is unusual in several respects. They appear across multiple independent measurement domains. They have persisted through multiple rounds of improved measurement. They show patterns of consistency with each other that are hard to explain if they arise from independent measurement errors. And they appear at a moment when theoretical frameworks for what the deeper physics might look like are more developed than at any previous time in the history of quantum gravity research. These characteristics shift the probability balance between the measurement and model interpretations in a way that justifies taking the model problem interpretation seriously alongside the measurement problem interpretation. The scientific community appears to be making this shift, slowly and cautiously as is appropriate, as evidenced by the growing number of papers exploring theoretical explanations for the tensions rather than purely observational strategies for resolving them. The growing investment in both the observational programs that will sharpen the anomalies and the theoretical programs that might explain them is the right response to the current situation. What would it feel like to be on the threshold of a major theoretical revision in cosmology? Looking backward through history, the answer seems to be exactly what we are describing, a period of productive uncertainty where the existing framework explains most things well, but strains at specific points that have resisted resolution through measurement improvement alone. The straining points multiply slowly. Theoretical alternatives accumulate. The community debates whether the problems are real or artifacts. Experiments are designed specifically to test the anomalies. And eventually, the accumulation of evidence tips the balance and a new framework emerges that explains both the old successes and the new anomalies. That process does not happen on a fixed schedule and cannot be predicted in advance. Sometimes the tipping point comes quickly after a decisive experiment. Sometimes it takes decades of gradual accumulation. The timeline depends on the nature of the underlying physics, the difficulty of the measurements required, and the creativity of the theoretical community in developing frameworks that make testable predictions. In the current situation, the timeline is genuinely uncertain, and intellectual honesty requires acknowledging that uncertainty rather than predicting either imminent revolution or indefinite continuation of the present tensions. What the holographic framework, emergent gravity, and quantum information approaches to spacetime share is a recognition that the standard description of nature as fields propagating through a smooth geometric background may be missing a level of structure that becomes important in specific regimes. That missing level is the quantum informational structure of spacetime, the way that the degrees of freedom of the universe are organized and correlated at a level below what the field theory description captures. In the language of the holographic principle, the field theory description counts too many degrees of freedom and misattributes their organization. The actual organization is holographic, with the bulk degrees of freedom being redundant descriptions of boundary data. If this is the right picture, then the cosmological constant problem, the Hubble tension, the dark energy evolution hints, and the early galaxy anomalies might all be different symptoms of the same underlying miscounting of degrees of freedom. The effective theory that serves as the standard cosmological model is an approximation that works well in most regimes, but overestimates the available degrees of freedom, and consequently makes wrong predictions in regimes where the holographic constraint is most binding. Those regimes happen to be the early universe, where densities were highest and the quantum gravitational structure was most relevant, and the current epoch, where the cosmological horizon is well defined and the de Sitter holographic effects are most significant. The missing ingredient in this picture is a complete and mathematically precise formulation of holographic cosmology that works for our universe, a de Sitter holography analogous to the anti-de Sitter holography of AD-SCFT. That formulation would provide a complete dictionary between the bulk cosmological description and the boundary informational description, allowing specific predictions to be made and tested. It would resolve the cosmological constant problem by showing how the vacuum energy arises from boundary degrees of freedom with the specific value determined by the holographic structure. It would explain the Hubble tension by showing how the effective expansion rate receives holographic corrections that differ between the early and late universe. It would explain dark energy evolution as the response of the effective cosmological constant to the changing entropy of the cosmological horizon, and it would constrain early structure formation by showing how the holographic bound limits the effective degrees of freedom available for matter to cluster in the early universe. This is a large program of theoretical work, and none of it is complete. The individual pieces are being developed by different groups with different emphases, and bringing them together into a unified framework is itself a major challenge. But the direction is becoming clearer as each piece develops, and the convergence of observational anomalies with theoretical motivations for the holographic approach to cosmology is one of the more compelling aspects of the current scientific moment. The universe appears to be asking the question that theorists have been trying to answer for decades, and it is asking it in the language of data rather than mathematical conjecture. The data will continue to arrive. Webb is still observing. DAISY is still mapping. The next generation of instruments is being built. The theoretical frameworks are being refined. And somewhere in the dialogue between observation and theory, between the photons arriving at Webb's detectors and the equations being written on blackboards around the world, the deeper picture of what the universe is and how it works is slowly coming into focus. Whether the current anomalies are the early glimpses of that deeper picture or the last wrinkles to be ironed out of an essentially correct effective theory remains to be seen. The honest answer is that we do not know yet. And that uncertainty, rather than being a source of despair, is the most honest expression of where science actually lives, at the boundary between what is understood and what is not, pressing outward into the unknown with the best tools available. The filter question, returned to from this vantage point, acquires a dimension that was not visible at the beginning. We have been thinking of the filter primarily in biological and civilizational terms, as a threshold that most lineages of life or civilization do not survive. But the holographic framework suggests that the physics of the universe itself may be more fragile than the classical picture implies. A universe whose fundamental description involves holographic degrees of freedom on boundaries is a universe where the bulk geometry, including the spacetime in which life exists, is an emergent and potentially fragile phenomenon. The conditions for the emergence of stable, persistent spacetime geometry over long timescales may be more restrictive than the conditions for the emergence of life within a given spacetime. If spacetime is emergent, and if the quantum informational structure that produces it can in principle be disrupted or changed, then the question of whether a given region of the universe remains a hospitable environment for complexity over long timescales depends not only on the local chemistry and stellar evolution, but on the stability of the underlying quantum informational structure. A universe that transitions between different holographic configurations might experience changes in its effective laws of physics, changes in the value of the cosmological constant, or disruptions of the spacetime geometry in specific regions. These changes might be smooth and slow, like the evolution of dark energy that Daisy is beginning to detect, or they might be sudden and discontinuous, like the bubble nucleation events associated with vacuum decay. The smooth changes are relevant to the long-term habitability of the universe, because changes in the effective laws of physics, even small ones, can have large consequences for stellar evolution, nuclear physics, and the chemistry of life over cosmological timescales. A cosmological constant that is slowly decreasing might eventually reach a value where the balance between attraction and repulsion changes character, affecting the long-term fate of gravitationally bound structures. A varying fundamental constant, if not tightly constrained by current observations, might drift over billions of years in ways that change the binding energies of atoms or the rates of nuclear reactions in stellar interiors. The discontinuous changes, vacuum decay events, are the most dramatic version of the filter at the cosmological level. If the universe is in a metastable state, the filter is always potentially present in the form of a bubble nucleation event that would propagate from its nucleation point at the speed of light, changing the laws of physics in its interior. The probability of such an event is exponentially sensitive to the height of the potential barrier between the current state and the lower energy state, and current estimates of that barrier height suggest the decay probability is negligibly small on cosmological timescales. But these estimates are model-dependent, and if the potential landscape is different from what the current effective theory suggests, the decay probability could be higher or lower by many orders of magnitude. The honest assessment of these cosmological-level filters is that they are too poorly constrained to contribute usefully to quantitative estimates of the great filter probability. The theoretical uncertainties are enormous, the relevant physics is not directly accessible to experiment, and the connection to civilizational survival timescales involves too many additional uncertain steps to permit reliable quantitative reasoning. But qualitatively, they remind us that the physical environment in which civilizations exist is not unconditionally stable. The universe is dynamic at every level, from the quantum fluctuations that are already being used to explain Hawking radiation and vacuum decay to the classical expansion that will eventually render the observable universe cold and dark. The window of time during which the physical conditions are hospitable to civilization, broadly defined, is finite at both ends, bounded on the past by the absence of heavy elements, and on the future by the heat death or vacuum decay that waits at the end of the cosmic timeline. Within that window, the great filter operates on the biological and civilizational timescales that are most immediately relevant to us. But recognizing that the window exists and is not infinite is part of the complete picture. The cosmological investigation we have undertaken is not primarily about threats to civilization. It is about understanding the physical reality in which civilization exists. But that understanding, when it is honest and complete, includes the recognition that reality is more dynamic and less unconditionally stable than the standard model's static cosmological constant implies. A more dynamical universe is not necessarily a more threatening one. But it is a more complex one, and complexity in the physical environment means more parameters that can shift in unexpected ways, more thresholds that can be crossed without warning, and more reasons to take seriously the question of what it takes to persist through the full range of physical conditions that the universe will provide. We have now traced the chain from Webb's early galaxy observations through the Hubble tension, dark energy evolution, fine-tuning, black hole thermodynamics, holographic spacetime, and emergent gravity. The chain is long and the individual links are of varying strength. Some connections are well-established physics. Some are serious theoretical proposals that are actively being developed and tested. Some are speculative extrapolations from the established and the theoretical into territory that has not yet been reached by either observation or mathematical proof. Maintaining clarity about which is important, and this film has tried to do that throughout. The established physics includes the Bekenstein-Hawking entropy formula, Hawking radiation, the thermodynamic laws of black holes, and the AD-SCFT correspondence in its mathematical form. These are well-tested results supported by extensive theoretical work, and in the case of AD-SCFT, by numerous consistency checks and applications to specific physical problems. They establish that black holes are genuine thermodynamic objects, that the information content of regions is bounded by surface areas, and that gravity and a non-gravitational quantum theory can be exactly equivalent in specific geometric settings. The serious theoretical proposals include the holographic principle as a universal statement about the information content of any region of spacetime, the idea that gravity is emergent from thermodynamic principles applied to horizons, the ER equals EPR conjecture, connecting entanglement and geometric connectivity, and the swampland conjecture that stable de Sitter vacua do not exist in consistent quantum gravity. These are not established facts, but they are grounded in the established results and have been developed by serious researchers with significant expertise. They are the directions that the field is currently exploring, and they make contact with observational questions in ways that could in principle be tested as the data improve. The speculative extrapolations include the specific claim that the cosmological anomalies are direct evidence of holographic corrections to the effective cosmological description, the proposal that the Hubble tension reflects quantum gravitational effects on the late-time expansion rate, and the suggestion that vacuum decay is a cosmologically relevant filter on civilizational survival. These extrapolations go beyond what the current theoretical frameworks can support quantitatively, and they should be understood as possibilities to take seriously and investigate rather than conclusions to accept on the basis of current evidence. The purpose of including all three categories in the same film is not to blur the distinctions between them, but to map the full territory from the established to the speculative, showing how the established results motivate the theoretical proposals and how the theoretical proposals motivate specific observational tests. Science moves in this direction, from the secure to the uncertain, from the tested to the speculative, extending the frontier of knowledge outward from what is known into what is not. Understanding that motion, and being honest about where on the spectrum any given claim sits, is part of what it means to take science seriously rather than treating it as a collection of established facts to be reported. The cosmological moment we are living through has a particular character that distinguishes it from earlier periods in the history of cosmology. Previous precision cosmology achievements, the establishment of the CMB temperature, the detection of CMB anisotropies, the discovery of cosmic acceleration, the precision measurement of cosmological parameters by Planck, were primarily about confirming and refining the standard model. Each successive generation of instruments tightened the error bars and confirmed the predictions in more detail. The current moment is different because the instruments are finding not confirmation but tension, not refinement but discrepancy. The direction of surprise has reversed. Instead of the universe agreeing with the model more precisely as the tools improve, it is disagreeing with the model more precisely. That reversal is the most significant thing about the current cosmological moment. Everything we have followed so far, the early galaxies that built themselves too quickly, the expansion rate that refuses to agree with itself, the dark energy that may be drifting, the spacetime that may be emergent from something deeper, converges on a single question that is both the simplest and the hardest question cosmology can ask. What is the universe, fundamentally, and why does it have the specific character it has rather than some other character entirely? That question has driven physics for centuries without producing a final answer, and the current moment suggests it will not produce one soon. but it is being asked with sharper tools and better data than ever before, and the shape of the answer is beginning to emerge even if the answer itself remains out of reach. The shape of the answer, as we have traced it, involves a recurring pattern. The universe appears to be organized around the relationship between information and geometry, between the quantum structure of states and correlations on the one hand, and the classical structure of spacetime and gravity on the other. Black holes force this connection into the open through their thermodynamic properties. Add SCFT made the connection mathematically precise in a specific setting. The holographic principle generalized it to a statement about the information content of any physical region, and the emergent gravity proposals developed by Jacobson, Verland, and others attempted to show how the specific form of gravitational dynamics arises from the informational structure of the underlying theory. If this pattern is correct, then the cosmological constant, dark energy, the expansion history, and the structure of spacetime are all aspects of the same underlying informational reality, described imperfectly by the effective framework of general relativity plus quantum field theory in curved spacetime. The imperfection of the effective framework is not a failure of physics. It is the expected behavior of any approximation scheme that works well in one regime and strains in another. The regimes where it strains, the early universe, the late dark energy-dominated universe, and the extreme environments of black holes, are precisely the regimes where the holographic relationship between information and geometry is most directly relevant. This pattern also connects, in a way we have not yet made fully explicit, to the question of time. Time in general relativity is a component of spacetime, a direction in a four-dimensional geometric structure, treated on equal footing with the three spatial directions up to a sign in the metric. Time in quantum mechanics is a parameter, an external label that tells the wave function when to be evaluated, not a dynamical variable in the same sense as position or momentum. This asymmetry between the role of time in the two frameworks is one of the deepest sources of difficulty in combining them into a consistent theory of quantum gravity. The problem of time in quantum gravity has been studied extensively and remains unresolved. In any approach where the metric of spacetime is a quantum variable, as it must be in quantum gravity, the notion of time as a fixed external parameter breaks down, because the metric includes the temporal component, and a superposition of metrics would be a superposition of time structures. The wave function of the universe, a concept introduced by DeWitt in the 1960s and later developed by Hartle and Hawking, is a function of three-dimensional spatial geometries with no explicit time dependence. Time in this framework is not fundamental but emergent, arising from correlations between different parts of the quantum state rather than from an external parameter. The emergent nature of time from quantum entanglement is precisely the kind of connection we have been exploring throughout this film. Just as space emerges from the entanglement structure between boundary degrees of freedom in add SCFT, time may emerge from correlations within the quantum state of the universe. The experience of time passing, of events occurring in sequence, of cause preceding effect, would then be derived properties of a quantum state that does not itself have a built-in temporal ordering. This is deeply counterintuitive because our entire experience of reality is organized around the flow of time. But it is the direction that several lines of theoretical argument point, and if it is correct, it changes the fundamental picture of what cosmology is describing. Cosmology, on this view, is not the history of a universe unfolding in time. It is the description of correlations within a quantum state that, when interpreted from the perspective of observers like us who are subsystems of that state, appears to have a temporal structure. Big Bang is not an event at the beginning of time. It is a feature of the quantum state that, from the perspective of internal observers, appears as a very hot and dense past. The future heat death or vacuum decay is not an event that will happen at the end of time. It is a feature of the quantum state that appears as a very cold and empty future when interpreted through the correlations that define our experience of time. This perspective does not make the cosmological anomalies less important. It makes them differently important. They are not just discrepancies between predictions and observations within the standard framework. They are clues about the quantum state of the universe, about which correlations are present and which are absent, about how the informational structure that underlies the geometric description is organized. The Hubble tension in this light is a question about the correlations between the early and late parts of the quantum state. The dark energy evolution is a question about how the effective geometric description of the quantum state changes as the correlations evolve. The early galaxy anomalies are questions about how the informational structure of the quantum state supports or fails to support the assembly of complex structures on specific timescales. The language becomes more abstract as we push toward the frontier, and that abstraction is unavoidable when discussing ideas that are at the boundary of what mathematics can currently formalize. But abstraction should not be mistaken for vagueness. The concepts are precise in the context where they have been developed, and the challenge is extending that precision to new domains rather than abandoning precision in favor of metaphor. The holographic principle is not a metaphor. Ad SCFT is not a metaphor. The Ryu-Takayanagi formula is a specific mathematical statement that can be used to make calculations. The emergent time picture has been made concrete in specific quantum gravity models. The difficulty is not that these ideas lack precision, but that extending them from the specific contexts where they are well developed to the general cosmological context where we need them is technically hard. The practical implications of this theoretical landscape for the near-term cosmological program deserve some attention, because the theoretical ideas we have been discussing should not remain disconnected from the observational work that is actually happening. The connection between theory and observation in frontier physics is always mediated by specific predictions, and the value of a theoretical framework is ultimately determined by the quality of the predictions it makes and whether those predictions are confirmed or refuted by data. The most immediate predictions that the holographic and emergent frameworks could make for cosmological observations fall into several categories. Dark energy evolution is the most directly testable at the current level of observational precision. If dark energy is not a true cosmological constant but a dynamical field, its equation of state differs from -1 and varies with redshift in a pattern determined by the underlying dynamics. Different theoretical frameworks predict different patterns of evolution, and sufficiently precise measurements of the distance-redshift relation and the growth of structure across a wide range of redshifts can discriminate between these patterns. Dacey's full survey, combined with Euclid and Roman, will provide precisely these measurements at the level of precision needed to distinguish between models if the deviations from lambda CDM are at the level currently hinted. Modifications to the growth of structure relative to general relativistic predictions are a second testable signature. If gravity is emergent from holographic principles, the effective gravitational dynamics at cosmological scales may differ from the predictions of standard general relativity in ways that affect how quickly matter clusters. These modifications would show up in the relationship between the expansion history, which determines how much volume is available for structure to grow, and the actual amplitude of matter fluctuations, which is determined by the effective gravitational dynamics within that volume. Weak gravitational lensing surveys are particularly sensitive to this relationship because they measure the projected matter distribution, which depends on both the clustering amplitude and the distance-redshift relation that converts angular positions to physical separations. The relationship between different cosmological probes provides another discriminating test. In lambda CDM, all probes should be consistent with each other once their individual systematic errors are controlled, because they are all measuring different aspects of the same underlying physics described by a fixed set of parameters. If the underlying physics involves holographic corrections that affect different probes differently, the tensions between probes would not be random, but would follow patterns determined by the correction's dependence on scale, redshift, and the type of physical observable. Mapping the pattern of tensions across many different probe combinations could reveal the structure of the underlying correction, even without identifying the specific theoretical framework that produces it. Primordial gravitational waves, if detected, would provide information about the quantum gravitational physics during inflation. The amplitude of the gravitational wave background, parameterized by the tensor-to-scalar ratio, depends on the energy scale of inflation and on whether the inflationary dynamics include holographic or quantum gravitational corrections. Some holographic inflationary models predict specific relationships between the tensor-to-scalar ratio and other inflationary parameters that differ from the predictions of standard slow-roll inflation. The detection of primordial gravitational waves by CMB-S4 or future space-based gravitational wave detectors, combined with precise measurements of the scalar spectral index from CMB experiments, could test these predictions. The statistics of the CMB beyond the power spectrum carry additional information about the primordial physics. Non-Gaussianity, the departure of the primordial fluctuation distribution from a Gaussian random field, is sensitive to the interactions of the field or fields that drove inflation. Different inflationary models predict different levels and types of non-Gaussianity, and holographic inflationary models have specific non-Gaussianity predictions that differ from standard inflation. Current constraints from Planck are consistent with Gaussian primordial fluctuations, but the sensitivity to non-Gaussianity will improve significantly with large-scale structure surveys like DAISY, Euclid, and Roman, which can measure higher-order statistics of the galaxy distribution that are related to primordial non-Gaussianity through the physics of structure formation. The 21-centimeter line of neutral hydrogen provides a unique probe of the epoch of reionization and the cosmic dark ages before reionization, a period that is not directly accessible to galaxy surveys or CMB measurements in the same way. Planned and future 21-centimeter experiments like the Square Kilometer Array will map the distribution of neutral hydrogen across a vast redshift range, tracing the history of reionization and the formation of the first structures with unprecedented detail. The 21-centimeter signal is particularly sensitive to the thermal and ionization state of the intergalactic medium, which depends on the timing and intensity of the first sources of ultraviolet and X-ray radiation. If the early galaxy anomalies seen by Webb reflect genuinely unusual early structure formation, that would leave signatures in the reionization history that 21-centimeter observations could detect. The cosmic neutrino background is another target for future experiments. Neutrinos decoupled from the rest of the cosmic plasma 1 second after the Big Bang, earlier than the photons that form the CMB, and they have been streaming freely ever since. They carry information about the conditions in the first second of cosmic history that is not encoded in the CMB. Measuring the cosmic neutrino background directly is extraordinarily difficult because neutrinos interact only weakly with matter, but indirect constraints on the neutrino mass sum from cosmological observations are becoming increasingly tight as surveys improve. A precise measurement of the neutrino mass sum would constrain the contribution of neutrino free streaming to the suppression of small-scale structure, potentially resolving some of the S8 tension independently of dark energy modifications. The stochastic gravitational wave background from early universe phase transitions and inflationary processes is another observational window into high-energy physics at early times. If there were phase transitions in the early universe at energies below the electroweak scale, they would produce a stochastic gravitational wave signal with a spectrum that reflects the temperature and duration of the transition. LISA, the planned space-based gravitational wave detector, will be sensitive to gravitational waves from electroweak scale phase transitions and from other sources in the millihertz frequency range. The detection of such a background would provide constraints on the particle physics of the early universe that are complementary to and partially independent of the CMB and large-scale structure constraints. All of these future observational programs share a common thread. They are pushing into regimes where the effective description of the standard cosmological model is being extended beyond its previously tested range, and where the holographic and quantum gravitational corrections to that description would be most visible if they exist. The convergence of multiple independent probes on the same physical regime increases the robustness of any detection of new physics, because independent probes carry independent systematic errors. A signal that appears consistently across multiple probes with different systematic risks is far more convincing than a signal that appears in only one probe, regardless of its statistical significance in that one probe. The relationship between the cosmological investigation and the search for extraterrestrial intelligence deserves a more direct treatment than it has received so far in this film, because the two topics are often discussed in separate contexts, and the connection between them is less explicit than it should be. The search for extraterrestrial intelligence is not primarily a search for radio signals or laser pulses from distant civilizations, though those are the observational methods currently in use. It is a search for evidence that complex information processing systems other than those originating on Earth have achieved and maintained the capability to transmit signals over interstellar distances. The absence of such evidence, combined with the apparent abundance of potentially habitable environments revealed by exoplanet surveys, is the Fermi paradox, and it is genuinely unresolved. The cosmological investigation changes the parameters of the Fermi paradox in several ways. First, the habitability estimates that enter the Drake equation are sensitive to the cosmological parameters. The long-term stability of planetary climates depends on the evolution of stellar luminosity over geological timescales, which depends on stellar physics that is in turn dependent on the fundamental constants. The availability of heavy elements for planetary chemistry depends on the stellar evolution and supernova history of the galaxy, which depends on the star formation history, which depends on the cosmological parameters governing structure formation. If those parameters are different from what the standard model predicts, the distribution of habitable environments in the galaxy is different from current estimates. Second, the timescales available for the evolution of intelligence are sensitive to the age of the universe and the rate of cosmic evolution. If the Hubble constant is higher than the early universe inference suggests, the universe is slightly younger for a given model of expansion, and the available time for biological and civilizational evolution is slightly shorter. The effect is small, a few percent at most, and is unlikely to be the decisive factor in the Great Filter question. But it is a reminder that the cosmological parameters set the stage on which biological and civilizational evolution plays out, and that uncertainty in those parameters propagates into uncertainty in the estimated abundance of civilizations at any given cosmic epoch. Third, and most significantly, the question of whether the physical laws and constants are stable over cosmic timescales is directly relevant to the long-term survival of civilizations. We have discussed this in the context of dark energy evolution and vacuum decay, but it is worth stating directly in the context of the filter. If the fundamental constants are drifting, even slowly, the physical conditions for complex chemistry, stellar stability, and nuclear physics are changing over timescales that could be relevant to civilizations with sufficiently long lifespans. A civilization that persists for millions of years would experience changes in the effective value of the cosmological constant, changes in the rate of expansion, and potentially changes in the other constants if they are coupled to the dark energy field through interactions that are not present in the standard model, but are predicted by some extensions of it. The possibility that fundamental constants might vary over cosmological timescales is not a new idea. Paul Dirac proposed in 1937, based on dimensional coincidences in the ratios of fundamental constants, that Newton's gravitational constant might vary with cosmic time in proportion to the inverse of the age of the universe. Dirac's large number hypothesis was motivated by coincidences rather than by a compelling theoretical framework, and subsequent observations have constrained the variation of the gravitational constant to be extremely small over the age of the universe. The fine structure constant and the proton-to-electron mass ratio have been constrained by observations of distant quasar absorption systems and by laboratory measurements of atomic transition frequencies over multi-year timescales. All current constraints are consistent with stable constants within the measurement uncertainties, but the constraints have finite precision, and the theoretical motivations for time-varying constants have grown more sophisticated since Dirac's original proposal. String theory and other quantum gravity frameworks generically predict additional scalar fields, called moduli, that couple to the standard model fields and determine the effective values of the fundamental constants. In the early universe, these moduli were dynamically evolving, and they may have settled to their current values through cosmological friction rather than reaching their true ground state. If the moduli are still slowly rolling in the current epoch, the fundamental constants would be slowly varying at a rate that might be below current observational limits, but detectable with improved instruments. The connection between moduli, varying constants, and dark energy is natural in these frameworks, because the moduli that determine the constants are scalar fields with potential energies that contribute to the vacuum energy. A modulus field rolling slowly in the current epoch would produce both a slowly varying effective constant and a contribution to the dark energy density that evolves slowly with time, exactly the kind of dark energy evolution that Dacey is beginning to hint at. The specific relationship between the rate of constant variation and the dark energy evolution depends on the coupling between the modulus and the standard model fields, and that coupling is model-dependent. But the qualitative connection is robust. If dark energy is a slowly rolling scalar field, and if that field couples to the standard model, the constants are varying along with the dark energy density. This connection, if confirmed observationally, would have profound implications for the long-term survival of civilizations. A universe in which the fundamental constants are slowly varying is a universe in which the physical conditions for chemistry, nuclear physics, and stellar evolution are changing on long timescales. The changes might be beneficial, pushing the constants toward values that are more favorable for complexity, or detrimental, pushing them toward values that are less favorable. Without knowing the direction and rate of the variation from a fundamental theory, we cannot assess which scenario is more likely. But the existence of the variation itself is a change in the physical environment that a very long-lived civilization would need to monitor and potentially adapt to. This is not alarmism. The current constraints on constant variation put the rate of change so small that the effects over any civilizational timescale, shorter than millions or billions of years, would be negligible. The point is that the cosmological investigation, by asking whether dark energy is truly constant and whether the fundamental constants are truly fixed, is also asking a question that is relevant to the very long-term future of any civilization that survives long enough for the answers to matter. The Great Filter operates on many timescales, from the biological and the technological to the geological and the cosmological, and a complete assessment of the filter requires considering all of them. The relationship between information, entropy, and the arrow of time provides another angle on the filter question that is worth exploring explicitly. The arrow of time, the fact that we experience time as flowing in one direction from past to future rather than being symmetric between past and future, is one of the deep puzzles of physics. The fundamental laws of physics are time-symmetric, or very nearly so. The equations of quantum mechanics, electrodynamics, general relativity, and even the standard model of particle physics are unchanged or very nearly unchanged under time reversal. Yet the world we experience is profoundly asymmetric in time. Eggs break but do not unbreak. Heat flows from hot to cold but not the reverse. The universe began in a state of low entropy and is evolving toward higher entropy. The low entropy of the early universe is the source of the arrow of time, as Boltzmann recognized and subsequent physicists confirmed. If the universe began in a randomly chosen state, it would almost certainly be in a high-entropy state, because high-entropy states vastly outnumber low-entropy states by any reasonable counting. The fact that the early universe was in a very low-entropy state, with the smooth, nearly uniform distribution of matter and radiation that the CMB shows us, is itself a remarkable feature of our cosmology that requires explanation. Why did the universe begin in such an atypical state? One answer is that the Big Bang was a special event in the history of the universe that set extremely specific initial conditions, including the low initial entropy, and that the laws of physics then evolved those initial conditions forward, producing the arrow of time we observe through the universal tendency of entropy to increase. But this answer merely relocates the question: why did the Big Bang produce such low initial entropy? A random initial condition would have produced high entropy, and we need to explain why the actual initial condition was so atypical. Inflation provides a partial answer. The inflationary expansion of the very early universe smoothed out initial inhomogeneities, producing the nearly uniform initial state that we observe in the CMB. But inflation itself requires a low-entropy initial state for the inflatoned field, so it does not fully solve the problem of why the initial entropy was low. It merely converts the problem of explaining low initial entropy in the large post-inflationary universe into the problem of explaining low initial entropy in the small pre-inflationary region where inflation began. The holographic picture offers a different perspective on this problem. If the information content of the universe is encoded on its boundary, and if the boundary is the initial or final surface of the cosmic evolution, then the entropy of the universe is bounded by the area of that boundary rather than the volume of the bulk. The initial entropy can be small if the initial boundary area is small, which is exactly the case for the early universe when the entire observable universe was contained within a region much smaller than it is today. The low initial entropy is not an inexplicable coincidence, but a consequence of the holographic encoding. The universe began with a small boundary area, and therefore a small maximum entropy, and it has been evolving toward higher entropy as the boundary area grows with the expansion. This picture is not complete, and it does not fully resolve the question of why the initial state was so uniform rather than being a randomly chosen low-entropy state. But it changes the character of the question from why was the initial entropy low to how is the maximum possible entropy determined by the boundary geometry, which is a question that the holographic framework has the tools to address at least partially. The arrow of time is relevant to the filter question because the arrow of time is what makes complex processes possible at all. Biological evolution, information processing, technological development, all of these processes are driven by the flow of energy from low-entropy sources to high-entropy sinks. Without the arrow of time, without the gradient between the low-entropy early universe and the high-entropy future, none of these processes would have a direction to exploit. The fact that the universe began in a low-entropy state and is evolving toward higher entropy is not merely a cosmological fact. It is the foundation of all complexity, all life, and all intelligence. The filter, at the most fundamental level, is set by the initial entropy of the universe and by the rate at which that entropy is increasing. If the holographic framework is correct, the entropy of the universe is fundamentally bounded by the area of its boundaries, and the initial low entropy reflects the small initial boundary area. As the universe expands, the maximum possible entropy grows, the actual entropy increases to fill the available capacity, and the gradient that drives complex processes is maintained over cosmological timescales. A civilization that understands this framework has access to a more complete picture of why complexity is possible and how long the window of complexity can remain open. The window is not infinite, because the expansion will eventually result in a state where all useful energy gradients have been exhausted and entropy is maximized within the available holographic capacity. But the window is also not so narrow that civilizations are racing against an imminent deadline. The timescales involved are cosmological, billions to trillions of years, far longer than the timescales of any biological or technological filter that civilizations currently face. This is actually a modestly reassuring conclusion within the framework we have been exploring. The cosmological filter, associated with entropy, and the arrow of time operates on timescales that are so long compared to civilizational timescales that it is not a relevant constraint for any civilization that is not already extraordinarily ancient. The filters that matter for the near-term question of why the cosmos is silent are the biological, evolutionary, and technological filters that operate on timescales of millions to billions of years, not the thermodynamic filter that operates on timescales of trillions to quadrillions of years. The holographic framework relocates the most distant filter further into the future, which is reassuring, while leaving the nearer filters just as uncertain as they were before. The question of consciousness and information processing in the context of this cosmological discussion deserves a brief but direct treatment. Consciousness is not a topic that physics currently has the tools to address in a complete way, and this film does not claim to resolve the hard problem of consciousness or to establish a physical theory of subjective experience. But the informational framework we have been discussing has implications for how consciousness is situated in the physical universe that are worth making explicit. If spacetime and gravity are emergent from quantum information, and if the universe is fundamentally a quantum informational system described by correlations between degrees of freedom on holographic surfaces, then the physical processes that underlie consciousness are ultimately informational processes at a fundamental level. This does not tell us anything about the subjective character of those processes, about why information processing is accompanied by experience rather than proceeding in darkness. But it does suggest that the physical substrate of consciousness, the neural information processing that biological organisms use to model their environments and make decisions, is an instance of the same kind of informational processing that underlies the structure of spacetime itself. This connection is not currently more than a suggestive parallel. The information theory of spacetime developed in the context of AD-SCFT is about quantum entanglement and geometric structure, not about the kind of classical information processing that neural systems perform. The quantum to classical transition, the process by which the quantum informational structure of the fundamental level gives rise to the classical information processing of macroscopic systems, is itself an incompletely understood process despite decades of work on decoherence and the quantum measurement problem. But the direction of the research, toward understanding consciousness as a physical phenomenon rooted in information processing, and toward understanding spacetime as an emergent phenomenon rooted in quantum information, points toward a future unified framework in which both are aspects of the same underlying reality. That unified framework, if it ever emerges, would represent the deepest possible answer to the question of where we are in the universe. Not just our physical location, our position in a galaxy in a cosmic web of filaments and voids, but our informational location, our position within the quantum state of the universe as a subsystem that processes information and experiences time. The filter question from this perspective becomes a question about which patterns of information processing are stable and self-sustaining, which configurations of the quantum state support persistent complexity, and what the quantum informational equivalent of the great filter is. These are questions that current physics cannot answer. They require a more complete theory of quantum gravity, a better understanding of the quantum to classical transition, and a more rigorous connection between the informational framework of fundamental physics and the information processing of complex biological and technological systems. The research programs that are working toward these answers are not converging as rapidly as the observational programs that are sharpening the cosmological anomalies. But they are progressing, and the combination of theoretical development and observational pressure from the cosmological anomalies may be what accelerates progress toward the answers. The universe has been running for approximately 13.8 billion years, and in that time it has produced the conditions for every complex structure we know of. Stars have formed and died, enriching the interstellar medium with the elements needed for chemistry. Planetary systems have assembled, and at least one has produced the conditions for biological evolution. That biological evolution has produced at least one lineage capable of building instruments sensitive enough to measure the expansion of the universe to 1% precision, to image the first galaxies, and to detect the gravitational waves from black hole mergers a billion light-years away. The scale of that achievement, from quantum fluctuations in the inflationary epoch to precision cosmological measurements in the current epoch, is staggering. And yet, confronted with the universe that those measurements are revealing, the honest response is one of productive uncertainty combined with genuine awe. The universe is larger, older, and stranger than any human civilization has previously understood. Its fundamental structure is less certain than we thought a decade ago, not because we have lost confidence in established physics, but because established physics has pushed us to the frontier where the established and the unknown meet. Webb and Dacey and the other instruments of the current era are not failing to confirm the standard model. They are doing something more important. They are revealing where the standard model's approximations begin to show their seams, and in doing so, they are pointing toward the deeper framework that will eventually replace the approximation with a more complete description. The filter question, returned to one final time, carries a different emotional register at the end of this journey than it did at the beginning. At the beginning, it was primarily a question about biological and civilizational survival, about what percentage of lineages that reach our current level of development continue past the bottlenecks that most do not survive. That question remains open and important. Nothing in the cosmological investigation has resolved it, and the silence of the cosmos remains as paradoxical as it was at the start. But the journey has added context. We are not simply biological creatures inhabiting a planet, wondering whether other creatures on other planets have survived the challenges of technological development. We are subsystems of a universe whose fundamental structure is still being worked out by both the universe itself and by the physicists who study it. The laws of physics that govern our survival are derived laws, effective descriptions of something deeper that we are only beginning to glimpse. The constants that make chemistry and biology possible may not be as fixed as we assumed. The spacetime through which we navigate is emergent rather than fundamental. The dark energy that drives the universe toward its eventual cold destiny may be a slowly rolling field that will behave differently in the future than it does today. None of these considerations makes the future more certain. Some of them make it less certain in ways that are unsettling. But they also make it more interesting, in the deepest sense of interesting, more full of genuine questions whose answers matter, more populated with territory that has not yet been mapped, more open to the possibility of fundamental surprises that change everything we thought we understood. A universe that is fully mapped and fully understood is not a universe in which curiosity has a function. A universe that retains genuine mysteries at its foundations is a universe that continues to reward the effort of understanding. The runners at mile 5 do not know what comes after the turn in the course ahead. They have never run this particular race before, and the markers are inconsistent in ways that suggest the map was made before the terrain was fully surveyed. Some will slow down and study the terrain more carefully before committing to a direction. Some will accelerate, betting on their current trajectory. Some will stop entirely, exhausted or injured or convinced the finish is not reachable. The ones who arrive at the finish, if any do, will be those who combine the willingness to continue with the capacity to update their understanding of the course as new information arrived. That combination, the continued motion and the ongoing update, is the best description of where cosmology and the search for our place in the universe currently stand. The motion continues, the data arrives, the understanding is updated. And the finish line, whatever it represents and wherever it is, remains ahead, beyond the visible horizon, in a terrain that is stranger and more interesting than the map we started with. The 7 chapters of this film have traced a spiral from the familiar to the radical. It began with the comfort of crowded star fields and the apparent abundance of worlds that might support life, and we end with the possibility that spacetime itself is not the fundamental fabric of reality, but an emergent description of something more basic, something organized around information and entropy and quantum entanglement. The journey passed through Webb's early galaxy anomalies, the Hubble tension, dark energy evolution, fine-tuning, black hole thermodynamics, and holographic spacetime. Each chapter tightened the spiral, revealing how the individual anomalies are connected to each other and to a set of deeper questions about the nature of the universe. The connections are not all established. Some of them are speculative. Some of the theoretical proposals we have discussed may be wrong, and the anomalies that motivated them may eventually be explained within the standard framework through improved measurements and better systematic control. Science does not guarantee that every set of anomalies points toward new physics. The history of science includes many cases where apparent new physics dissolved under closer scrutiny, and it also includes cases where it did not. Distinguishing between these cases requires exactly the kind of sustained empirical and theoretical work that the cosmological community is currently engaged in. What the journey has established, though, is the coherence of the questions. The question of whether the universe is built from spacetime and fields in the conventional sense, or from something more fundamental organized around information and holographic principles, is not a question that emerged from a single anomaly or a single theoretical insight. It emerged from the convergence of multiple independent lines of evidence and multiple independent theoretical developments, all pressing toward the same frontier from different directions. That convergence is what gives the question its scientific weight and what justifies the investment in the instruments and theoretical programs that will eventually answer it. The great filter, throughout this journey, has served as both a frame and a destination, the question that motivates the journey, and that the journey is meant to illuminate even without fully answering. The filter is real in the sense that the cosmos is silent despite the apparent abundance of potentially habitable worlds, and that silence requires an explanation. The filter is uncertain in the sense that its location, whether behind us or ahead of us, remains unresolved by any current evidence. And the filter is connected to the cosmological questions we have been exploring in the sense that the physics of the universe, including its fundamental structure, its expansion history, and the stability of its laws, sets the stage on which the filter operates. A civilization that understands its cosmological situation more completely is better positioned to assess the filter question. Not because cosmological knowledge directly resolves the biological and civilizational aspects of the filter, but because it provides the physical context within which those aspects must be evaluated. A civilization that knows whether dark energy is constant or evolving, whether the fundamental constants are stable or drifting, whether spacetime is truly fundamental or emergent from something deeper, has better information about the physical environment it will face over the very long term. That information is valuable even if it cannot be acted upon immediately, because understanding the physical landscape is the prerequisite for navigating it wisely. We are building that understanding now, with Webb and Dacian Planck and the theoretical frameworks of holography and emergent gravity. The understanding is incomplete and will remain incomplete for the foreseeable future, but it is advancing, and the direction of advance is becoming clearer. The universe is stranger than we thought, and that strangeness is an invitation to understand it more deeply, to build the instruments and the theories that can resolve the current ambiguities, and to follow the chain of implications wherever it leads. The photons from the earliest galaxies are still arriving at Webb's detectors. The spectra of millions of galaxies are still being measured by Dacy's robotic fibers. The equations of holographic spacetime are still being written on blackboards and in notebooks around the world. The journey is not over. The race is still running. And the finish line is still somewhere ahead, in terrain that is more complex and more interesting than the map we started with, waiting to be reached by those who keep moving and keep updating their understanding of the course. That is the most honest place to end, not with a conclusion, because the conclusion has not yet been reached, not with despair, because the questions are answerable in principle, and the tools to answer them are being built. Not with false certainty, because the current uncertainties are genuine and important and cannot be wished away by narrative convenience. But with the recognition that we are alive in a universe that is stranger and more interesting than we knew, with instruments sensitive enough to detect that strangeness, with theories sophisticated enough to begin interpreting it, and with enough scientific integrity to follow the evidence wherever it leads, even when it leads somewhere unexpected. The universe did not stop surprising us when we built better telescopes. It surprised us more because better telescopes see more, and more seeing means more territory where the unexpected can appear. James Webb is the best telescope we have ever built. And it is showing us that the universe we thought we understood is more mysterious than we realized, more dynamic than the simplest model implies, and more full of genuine open questions than the precision cosmology of the last 20 years had suggested. That is not a failure of cosmology. It is cosmology working at its best, reaching the frontier of knowledge and finding that the frontier is further out and more interesting than the map suggested. We are at mile 5. The crowd is real. The markers are wobbling, the terrain ahead is unmapped, and the instruments that will map it are already looking at the sky. The silence of the cosmos is not the final word. It is a question, and questions have answers. The answer to why the cosmos is silent, to where the filter lives and what it demands, to whether we are early or lucky or both, will not come from a single instrument or a single theory or a single generation of researchers. It will come from the long accumulation of precisely measured photons and carefully developed mathematics and the honest willingness to revise what we thought we knew when the evidence demands it. That accumulation is underway. The silence is being listened to more carefully than ever before, and somewhere in its texture, if we build the right instruments and ask the right questions, the answer is waiting. The race continues. The universe continues. And the work of understanding it continues with the same mixture of wonder, precision, and humility that has always characterized the best of human inquiry into the nature of things. That is not a small thing. In a universe that may be 13.8 billion years old and 93 billion light-years across, the fact that any part of it has developed the capacity to understand itself, to measure its own expansion, to map its own structure, to ask why it exists in the form it does rather than some other form, is perhaps the most remarkable fact about the universe that we currently know. And what it means, what it implies about the relationship between the universe and the intelligence that has arisen within it, remains one of the deepest questions any civilization can ask. We do not know the answer, we know the question, and that is where all good journeys begin.